Hey guys, welcome back. This is chapter 20, the second and final chapter on midterm 2, 118C. And chapter 20 is a direct follow-up on chapter 19. In that chapter 19 talked a lot about this guy, right? The carboxylic acid. And we sort of explored how to convert it into different other different molecules, the acyl halide, the anhydride, ester, and the amide. And we sort of said, hey, all these guys share a certain quality, right? They share the fact that they have a carbonyl. And they have this special Y group. That's what makes these guys all inherently different from chapter 17-18's ketone and aldehyde. So we're going to begin chapter 20 with the study of, okay, now we know how to make them, right? But what do we do with them? Now, a little bit of reminder that not only can the carboxylic acid become these guys, right? It can be turned into all of these family members, but the family members all have a relation back. Okay, so this was the carboxylic acid derivative family. There's also another one, right? A little bit far removed, the nitrile. And the nitrile might seem a little insignificant, but the nitrile can be turned into a carboxylic acid, as we saw in 118B. So although it's farther in the family, a little bit removed, it still has the same blood as everyone. Okay, so we're going to go ahead and start off this chapter, looking at the different derivatives. And before we even get into the reactions, look at the structure and what the structure can simply tell us, about these guys before we even react with them. So we have the acyl halide, acyl anhydride, acyl ester, and the acyl amide. And so you'll notice two things. One, I did a methyl ester. That's insignificant. Could have been any kind of ester. But this dimethyl amide is actually really important. And we'll discuss a little bit later why it's important that I made this decision to specifically use this one. All right. So again, very first thing we want to examine here is the fact that, well, one, these guys have the same kind of carbon. They all have the carbonyl. But attached to that carbonyl, that's not what I'm meant to do. Attached to that carbonyl is a Y group, right? This interesting Y group here. And the Y groups are all a little bit different. Otherwise, if they're the same, they'd be the same derivative. So they have to be different. And the one thing we want to assess about these guys is, well, remember in the carboxylic acid, how we said the carboxylic acid's Y group allowed it to do nucleophilic acyl substitution, right? So it's able to do nucleophilic substitution where we could turn that OH into something new via substitution. Well, let's assess all these groups and their ability to be substituted, right? Or their ability to act as a leaving group. Because if they're substituting, they must leave. So they must have pretty good leaving group ability if they want to do that. Okay, so we have chlorine minus, acetate minus, methanol minus, and dimethylamine minus. Okay, and maybe right off the bat, you kind of notice something, right? All the way on the left here, we have Cl minus, which hopefully by now you remember from 118A, 118B, chlorine is one of the better leaving groups, right? The halides in general, X minus in general, is just really good at leaving, right? Not only are they really large, but they're also fairly electronegative. So charge likes electronegativity, and they like a lot of surface. So signs electronegativity working out there. And in general, chlorines tend to clock in about -5. Okay, -5 in pKa. So these guys are fairly acidic. Okay, and therefore they're going to be really good leaving groups. At least when we look at the other groups here, clearly it's the best one. Following really quick up, right, is the acetate, which we just learned in the last chapter video, chapter 19, that acetates, or any carboxylic acid really, has a pKa of 5. Okay, and this is like a pretty, you might think it's a pretty big jump, -5 to 5, it's like 10 units, but it's still fairly acidic, right? The minus charge is still being fairly delocalized and stabilized by 2 oxygens, although not as well as the chlorine, but still possible to stabilize. And these two here are what I would say are pretty good leaving groups, right? 5 and -5, yeah, 5 is not great, but it's pretty good, especially when we compare to the methoxide here, which you might remember. If you don't, it's okay, I'll tell you. Most alcohols, their conjugate bases clock in about 15. And 15 is really when we're calling the line on basic, right? Like you might remember 0 to 14 pH scale. 14 is what we call basic. So if something's at 15, you best believe it's pretty basic, right? And so this 10-unit jump is very clearly different from this 10-unit jump. And so we can kind of see that we kind of go from fairly acidic to kind of basic, pretty basic. And then when we look at the amide ion, which clocks in about 35, this is super strongly basic. So the very first trend we can kind of see arising from these derivatives is as we go to the right, or as we go from acyl anhydride to, acyl acid to amide, we can see that the leaving group ability gets worse, right? The better leaving group is the acid and chloride, and then the worst one is the amide. Okay, so we can see this trend coming out of the reaction, or sorry, out of these derivatives. Okay, and also another thing that you can kind of keep in the back of your mind is, again, I mentioned that these are fairly acidic and these are fairly basic. You can kind of draw a line over here where we can say that these are, again, fairly acidic and these are fairly these are fairly basic. Okay, it's fairly acidic and fairly basic. Okay, and this is going to come into play when we think more about reactivity and what we need to do to get these derivatives to react by understanding this here. Okay, I'm actually going to say, write this down if you have to. I'm going to erase it because you'll see very soon enough. Actually, we'll keep it for now. If we need to erase it, we will later. Okay. Now, another thing we can kind of pull out of, right, leaving group ability, right, or something that we can also assess is the fact that, hey, remember in the carb acid, again, we noticed the carb acid had this Y group and we said that group could leave. Well, there was something else very significant about this Y group. It's the fact that it had electrons. Now we have a pi bond here. So we have 2 p orbitals and we have a heteroatom with electrons. Notice that we have 3 p orbitals next to each other. What happens when 3 p orbitals next to each other? They conjugate, they add together, and resonance is born. Okay, so another thing is that the Y group can participate in resonance with its carbonyl. So all of these derivative Y groups do have electron lone pairs. And actually I would even say you can get ahead of me here, but you can think about which derivative you think is the better donator and which one is the worst. Okay, essentially what we're asking ourselves is, how likely is this to happen? This, and this. Okay, so maybe take a second and try to answer this yourself. Maybe pause and see if you can figure out which one is more likely to donate. Okay, but the one thing that I would look at first is, again, if something is donating electrons, it can't necessarily have a deep affinity for them, right? Another way of thinking about this is that if I kind of label out the atoms here, right, and remind you guys that electronegativity increases this way, electronegativity is a tendency to want electrons, to keep them, right? If you have electrons, you really want to keep them to yourself. So if things to the right are more electronegative, like oxygen, chlorine, how likely are these guys to keep their electrons? Probably very likely. They really want to keep them. Compared to nitrogen, right? Compared to nitrogen probably is okay with giving away its electrons. The broader sort of implication here is that when I look at chlorine, oxygen, and nitrogen, right, the atom that stands out to me is nitrogen, because nitrogen, being the least electronegative, right, is going to donate more likely into the carbonyl. Okay, it's way more likely to donate into the carbonyl. And so we can actually form a resonance form out of this. Okay. We actually do this for all these guys. And, we can kind of see here like, hey, N plus, O plus, Cl plus, which atom carries that plus the best? It's going to be the amide. So it's highly likely that the amide is going to be the most, donating, has the highest level of resonance. And so we can sort of start our resonance line here. Now, again, as we move to the left, right, resonance should decrease, right, if we're saying the amide is the most resonating. And that does make sense to us, right, because again, oxygen and oxygen here, they're always going to be less donating than a nitrogen. So it's not very likely that they're going to be very resonant active. And chlorine here, actually, here's a little cool thing about chlorine. If you think about chlorine, right, so this is row 2, this is row 3, right? A pi bond is consisted of p orbitals, right? So carbon and some X atom here, right? There needs to be p orbitals that add together, right, for us to have resonance. If you think about row 2, right? Row 2 has 2p orbitals, right? 3p orbitals for row 3. 2p orbitals are essentially the exact same size, right? Because they're both 2p. So when X here is equal to carbon, nitrogen, oxygen, or even fluorine, really, the orbital overlap should be really great and resonance should occur, right? Because the orbitals same size, they add together really nicely, okay? Well, when X is actually chlorine, which again we said was a 3p orbital atom, larger orbital just like that, how do you guys feel about that overlap, right? How does this overlap look like? To me, it looks pretty garbage, if I'm being honest, right? It doesn't look very good. Like, how's it going to add, right? It's going to add like that, add like that. That's not really good at all. The orbitals are not really aligned well. And orbital alignment is very important for any kind of bonding. So in actuality, it's not very smart to say that the chlorine is going to be resonating a lot with the carbonyl. In fact, we can almost even say it doesn't resonate at all. Okay, so it is devoid of resonance effects. So it can almost even get rid of the resonance form that we had drawn earlier. And so it becomes very clear now that, hey, between the amide and the acyl halide, where we have the most resonance and least resonance, right, this trend line is very well made. Okay. Now, one interesting little tidbit that people tend to get a little caught up on is they see that the anhydride is less resonating than an ester. And I think some people kind of get caught up and they think, wait, that doesn't make sense because wouldn't an ester don't have the ability to donate to the left and the right, so it has more resonance? Well, think of it this way. If we compared, like if we looked at just one carbonyl, right? So this has one carbonyl and we'll look at this one carbonyl. The ester oxygen can donate 100% into one carbonyl. Right? It donates 100% into one carbonyl. So this carbonyl is always going to be electron rich, and electron enriched by the oxygen. On the other hand, this carbonyl can be electron enriched, but so can this guy as well. There's constant competition between both carbonyls to get electrons from oxygen, and that in itself results in a little less commitment of electrons. So you can think maybe 50-50 in terms of where electrons are going. That essentially tells you guys, oh, right, if there's less electrons going to this guy, like less of the time and less time to this guy, right, they're splitting up the time with electrons, it is less resonance active on one carbonyl. Although there is two carbonyls, so in a sense, I guess you could say it is like a little more resonating, but it has to split up its resonance between two carbonyls as opposed to every other derivative has only one. Okay, so that's why the anhydride is always less resonance active than an ester. Okay, and again, the acyl halide, as we said, doesn't really have a resonance form. So it's the least resonant active. Now, one thing you might notice in this resonance trend is that there is, again, the Y group carries a cation and the carbonyl oxygen carries a minus. So if we have an O minus, we know O minus are basic, they like protons. I wonder how the basicity of these guys relates. So maybe try this trend on your own too, right? How would you say the basicity, which way does the basicity go on the derivatives? Okay, and so this is always a pretty hard question, right? You have to kind of synthesize a lot of information that we talked about. But again, if the point is that the O minus here, right, the O minus here, and the lack of an O minus here, right? The O minus is what's picking up the electrons, or sorry, the proton. We have to think about, hey, how strong is this O minus in the total hybrid character of the structure, right? And how would that relate to basicity? So I think we can all agree, right? The more O minus character there is, the more likely that O minus is to pick up a proton, because again, O minus is basic. So ask yourselves, of these derivatives, who has the strongest O minus character, right? Essentially, which of these derivatives will have more of their resonance form in the overall hybrid? Okay. So again, tough question. Some, if you really think hard about it, but remember, the more resonance we have, the more the hybrid has all the character of the other resonance forms. So essentially, if nitrogen is the most resonating, it has the most character of its resonance form. It has more of this O minus character in the overall hybrid. Okay, one more time. Amide is the most donating, right? It's the most resonance active. Therefore, it has more of its resonance form character leak through in the hybrid. It has a stronger O minus. It is therefore the most basic. Okay, and you can kind of see it here too, right? The fact that amides has the most O minus, acyl halide doesn't even have an O minus, right? It doesn't even have an O minus because it doesn't have a resonance form. So if it doesn't have a resonance form and no O minus, how can we say that the acyl halide is more basic than the literal, O minus on any of these guys, really? Okay, so basicity is also going to correlate with resonance, right? And that should make sense, right? More resonance means more O minus, means more basicity. Sorry, my lines are not good today. There we go. I like this one. So we have a higher basicity. Okay. And there's like sort of another, you kind of notice that resonance does help us quite a bit, actually, for all these trends. But there is another thing we can think about when it comes to resonance, if it's not, if it's also not basicity. One other thing we can think about is, well, if we're thinking about the character of the resonance form bleeding through in the hybrid, you might notice that, between these guys, not only is the charge a difference, right? That this is neutral and this is minus and plus, but there's also significant double bond and single bond character that we have to consider, right? Like when we think about the bond length of, let's say, the CY bond, right? It can either be a double bond or a single bond, right? Because it's a single bond here, it's a double bond here. So using resonance, again, try to explain to yourself why might the amide have, a shorter or longer bond, right? Think about that for a second. Why might that be? So first, you have to answer the question of, does it have a short or a long bond? And to answer that question, we have to look at resonance, right? So there is a single bond and a double bond available, right, in the overall hybrid. Again, we have to ask ourselves the question of how much does the resonance form character bleed through in the hybrid? Because the more that this exists, the more double bond character exists in the overall molecule. I guess one thing that could have been a good reminder is that a single bond is longer than a double bond, which is longer than a triple bond. So the more of this double bond character that exists, the shorter the bond should be, because it has, that short bond character as opposed to long bond character. So if the amide has the most resonance, and right, that resonance involves a double bond, it has the most double bond character, it should also have the longest CY bond out of all of these guys. So I'll write it like this. It should have the longest CY bond character, right? Because it has the most of the double bond leak through in its hybrid, as opposed to the ester and the anhydride, which have oxygens. And again, chlorine doesn't even have a resonance form, really. So it has the most single bond character, and single bonds are longer than double bonds. You can also pull out another one, which is, hey, if we're looking at the CY bond, let's look at the CO bond, and we can do that, right? And it's sort of the same logic, right? In the resonance form, it's also in the original form, it's a double bond. Resonance form is a single bond. How much of the single bond character leaks through? If the amide has the strongest resonance form, right, the one that leaks out the most, it should have the most of the single bond character. It should also have the, oh, sorry, I drew this the other way. It should be the other way. My bad. The longest bond should be this way. But like I was saying, if the amide has the most of this resonance form bleed through, and that resonance form involves a single bonded O, right? It should have the most single bond C single bond O character, and it should have the longest C double bond O. Now, here's an interesting little tidbit that I'll teach you guys about, even though you don't need to really know it, but I think it'll help. There actually is an accepted resonance form of the acyl halide, and it looks like this. Essentially, the acyl halide is so polarized, right? The chlorine is so like inductively withdrawing that actually sometimes people believe that this is actually an acylium ion and a chlorine anion. Well, essentially what it's saying is that the CY bond is so far apart, the electrons are so polarized, they're not really covalently shared. It's actually more of an ionic pairing. And so if the electrons are so on chlorine that chlorine could possibly leave, right, this should be the longest bond. So another reason why this is the longest bond, because some people consider it to actually not be an acyl halide, but an acylium ion and a chlorine anion. Another thing is you might remember the acylium ion has an interesting resonance form. It has the triple bonded oxygen. And so if there is a triple bond in the carbonyl, right, triple bond is the shortest bond possible, it makes sense that this CY bond, or sorry, this CO bond is the shortest, right? It is literally the shortest one. This one here is the shortest because it's the only derivative with triple bond character available in its carbonyl. We can actually, if you can actually use IR as well to explain this, right? Because in the IR, the acyl halide is the bond that's most to the left of all the carbonyls, and so that means it's a higher, it has a higher bond bond order available to it, which is that triple bond character. Okay, so a lot of things that we can kind of pull out of just a structure. Okay. Now, there is one more thing. Oh, actually, before we get to that, we've talked a lot about resonance and bonds and all that. You guys should remember the makeup, right? The sigma and pi makeup of the bonds. So I'm going to go ahead and remind you guys of those things. Okay. But if we were thinking about like the CY bond, right, you guys should remember that the CY bond is either going to be made up of carbon and halogen, or carbon and oxygen, or carbon and a nitrogen, or carbon and a carbon. But when it comes to these guys, I guess I'll just do it like this. Just remember that when it comes to sigma bonds, carbon and nitrogen use hybrid bonds. Okay, so like sp2, sp3, sp, depending on how many pi bonds it has. Halogens and oxygens, however, use their p orbitals. A couple of you are probably pulling your hair out because you just learned in 118A that, Leavens told you that, hey, oxygen's hybridized. Well, we're in a series class, and Nasiri is convinced that oxygen doesn't, so we should now be convinced as well. Hopefully you also remember that pi bonds in general are just, p orbitals. So if you're ever asked to like label, right, what the orbital makeup of a bond, just keep in mind these things, right? Like the orbital, like let's say we're thinking about the sigma makeup, orbital makeup here, right? That's going to be a CsP2 because it's double bonded, and then it's going to be an OP because oxygen uses p orbitals always when it makes bonds, right? Oxygen always uses a p orbital when it makes bonds. Carbon is going to make a hybrid, or use a hybrid orbital for a sigma, and a p orbital for a pi bond. But if we were looking at the makeup here on the sigma bond, that would be CsP2 and NsP2, right? Because carbon and nitrogen hybridize and make their sigma bonds out of hybrid orbitals. So something to keep in mind in case you had forgotten. Okay, cool. Now, a while ago, we talked about basicity, right? We talked about the basicity of carbonyl compounds, or sorry, of these acyl derivatives. But we never really talked about acidity of these acyl derivatives. And so we can actually also consider how acidic these guys are. And you might be wondering, well, where in the world would we look for that? Don't worry, we can look here, right? Because if you remember, on ketones and aldehydes, the alpha carbon, which is this guy here, the alpha carbon was particularly acidic. So we could pull off a proton and form these anions here. And so the question is, how acidic are these anions? Well, it turns out the best way to explain this is to, again, look at the resonance forms. Okay, so I want you guys to look at these resonance forms. And the one thing that I will tell you that hopefully you're realizing is that, at least for the anhydride, ester, and amide, this is a really ugly resonance form, right? There's 3 charges. Notice how there is a dianion really close to each other. You know, dianions, repel each other. There are, cations. You can tell these are not very good. So if these resonance forms are not very good resonance forms, right? How can, they explain to you which one of these is most acidic? Okay, so maybe take a minute and try to explain that to yourself, or try to explain it. Now, if you tried, good for you. I know that it's a fairly difficult thing to do. I'm going to get rid of this now because it's a little bit cramped. It's a fairly hard thing to do. Okay, so don't worry. But what I want you guys to realize again is that these resonance forms are like destabilizing resonance forms. We've seen that before, right? Remember in benzoic acids last chapter, when like there would be, like, let's say OCH3 here, and there'd be a carboxylic acid. Remember how this anion destabilized the acidity of this proton? That's essentially what's going on in these guys here. It's this one resonance form that is destabilizing the anion. So if this one resonance form is destabilizing the anion, and specifically it's the resonance form where the Y group donates electrons in, then the question just becomes, how donating is that Y group to make this resonance form and further destabilize the enolate molecule? So another way, I guess an easy way to rephrase it is, if this is the bad resonance form, then, more resonance would mean that more of that, more of this resonance form leaks through in the hybrid. So who is the most resonating guy? Remember, the green line here says it's the amide. That means that the amide has the most character of this bad resonance form. And the more of this character we have, the worse the enolate is overall. So the acidity is essentially, again, just going to follow, right, resonance, or it's going to go anti-parallel to resonance, because the more resonance we have, the more of this bad character we have, right? And the amide has the most of this character. So the amide has the most of this destabilizing form, as opposed to the acyl halide, who has no resonance, essentially, has none of that bad resonance form, and therefore is the best enolate because it has no destabilizing effect whatsoever. Okay, so in terms of acidity, very much in this direction. Okay, and actually I can give you guys values. Oh, I should have given you guys values for basicity too. But I can give you guys for acidity here. Okay, this proton tends to be around, we say 15. I'm going to put quotations here. I'm going to say about 20, and I'll explain why a little bit, why I'm doing that. Ester is going to be about 25, and the amide is about 30. Okay. Now on the ester and the amide, there is another proton we could consider. It's these guys here. I want you guys to realize though, is that these guys are sp3 sp3 anions, whereas the alpha carbon is an sp2 anion because it resonates, right? So this is sp2. Anion here would be sp3. These guys are always going to be worse than the enolates, right? These proton positions here are always worse. The only thing that makes them more or less acidic than each other is going to be inductive effects. So how inductively, how much can this oxygen here or nitrogen here inductively pull on the proton? So actually, I'll put it in this color here. Right. By the way, I know that there's a lot of trends going on here. I am forced to put them all on the same page, but feel free to separate these however you want and organize it to your benefit. I can only just do it on one page. That's why I'm doing it on one page. But really, it depends on how how strong the inductive effect is going to be, right, to stabilize that anion. And so if you think about it, oxygens have a stronger electronegativity, stronger pull. Their dipoles can be a lot larger as opposed to nitrogen. So if you wanted to give a value, I will give you an arbitrary value. I'll give you the value. Let's say this is 49. Sorry, let's make this 48. And we'll make this 49. I don't really actually even know what they are, but it's just to show you that, hey, the ester carbon right there, that will have a higher acidity simply because of inductive effect as opposed to amide. Okay, so so much information we're able to pull out of the carboxylic derivatives. Okay. And one thing I want you guys to notice here is like a lot of these guys, 3 of these derivatives were highly reliant on resonance. So notice how these guys, we kind of used resonance, right, a lot to explain everything. Not that we didn't use the acyl halide, but the acyl halide didn't, we used the lack of resonance to explain why the acyl halide was so like polarized in all of these decisions, right? So if resonance dictated a lot of the effects in these guys, then we can kind of say that, induction explains a lot of the effects that we see in the acyl halide. And don't forget, the acyl halide is not the only inductive effect, carbonyl. There are 2 more, right? The ones we talked about in chapters 17, 18, right? The aldehyde and the ketone, right? These guys are also implicated in a lot of these trends, although some of these don't really make sense, right? Like resonance, labeling group, CY length, CO length works though, acidity works though. We do know that aldehydes are more acidic than aldehydes are more acidic than ketones, right? This H tends to be around what, like, we'll give it 17. This H here tends to be around like 19. Okay. And again, if these guys are dominated by induction, right, there's only inductive effects going on, then they should be grouped together as opposed to resonance effects. Okay, so this is always a bit of a tricky one, but for these trends that we have on the page, we are going to say that the aldehyde and the ketone are more analyzable than the anhydride. Okay, because of, again, what we talked about in terms of resonance and induction. Although I'll talk a little bit more on the next page about how that's not always very true. Now, there is one derivative we didn't really give a lot of attention to, but there is a nitrile. Now, the nitrile is interesting because when we look at bond length here, or when we look at the trends here, so resonance doesn't really make sense to talk about. Leaving groupability doesn't really make sense to talk about, although you'll see that the nitrile is actually another derivative in disguise. So we will talk about its leaving groupability eventually. But acidity is something we can talk about. So it turns out nitriles have acidity of 25, which makes them very similar to esters. So everything we talk about esters in terms of their acidity will also be applied to nitriles. Basicity wise, so how basic are, is this group here? This is an sp amine, and you might think that a nitrogen that's sp might be more basic than an oxygen because it's nitrogen versus oxygen, but because it's sp, it's actually very, very non-basic. This is a negative integer, okay, a very, very negative integer. Actually, that's kind of funny for me to say because all these are negative integers, but we can think it's like -10. It's so non-basic. It's super hard to pronate a nitrile because it's an sp amine. Okay. In terms of, I guess we can go with C. Oh, well, I guess it doesn't really matter, but the bond length here, that's a triple bond, right? So this here is a triple bond. So it is going to be the shortest out of all of them. Because remember, single, double, triple is the smallest, right? So for the nitrile who has true triple bond character as opposed to the acyl halide, always going to be the shortest in the nitrile there. It's not really a CY or a CX, so, or sorry, CY or a CO, so that's why it's hard to put a color on it. I think I'm just gonna go like this. This is the shortest one. Okay, but yeah, that's pretty much the trends that we can pull out just looking at these guys, right? Just looking at these guys. Now, again, I mentioned at the very beginning that I made a very significant choice picking, the the dimethyl amide here as opposed to any other amide. The ester didn't really matter, but the amide really did. And the reason for that is because, oh, actually, before we move on, one more thing. There's basicity numbers. I should give you 2 because I gave you the -10 here. So this is going to be negative, or this is like 0. This one's 0. This one's like negative 6, I want to say, -7. And then these here are like -8. Both of these, they're like slight deviations of -8. This guy's like -9. Okay, so those are basic numbers. But back on to what I was saying, I mentioned before that I specifically chose not to use certain amide. And it's because when we look at this amide, right, you might have expected me to draw this amide here. Okay, and this amide here is very important to distinguish from this amide because of those hydrogens here. So these hydrogens here are what I was trying to avoid. And the reason for that is because, think back to the carboxylic acid, right? Remember when we talked about reactivity of the carboxylic acid, and we talked about basic and acidic nucleophiles? Acidic nucleophiles, it didn't really matter that this was an acid, but when it came to basic nucleophiles, right, the reactivity suddenly changes very drastically. So acidic nucleophiles tend to attack here, right? But basic nucleophiles attack at the proton, right? So the reactivity is very skewed because, again, carboxylic acid, it's in the name, it's an acid. It likes to give up that proton very, very easily. The amide is no different. And so, if the carboxylic acid has a pKa of 5 here, the amide, right, has a pKa around 15 on that proton. So a good amount of bases can pick up this proton, especially like alkoxides or hydroxides. Amine anions can definitely easily do it. And so it's really hard to talk about a general reactivity of all these derivatives without getting things a little bit mixed up. So I'm going to try to do that right now. Show a general trend of the reactive derivatives. Actually, let's do it this way. Let's put the derivatives first. Again, you might have thought on the other page when I talked about leaving groupability that I was talking strictly about, reactivity. And I kind of was, but not necessarily, because we'll see that it kind of changes a little bit. What we wrote here is a little different from what we're going to write here. Okay, so again, in terms of how they're in order now, right, we can see a general reactivity trend, right? And this was basically all about leaving groupability. But when I add in the carboxylic acid, for example, right, carboxylic acid is going to go here, right? And specifically, it's going to go here whenever we're in a basic solution, right? Because the reactive component is going to be this proton. Same thing with the amide. Right, same thing with the amide. Whether it's primary or secondary, shouldn't matter too much. Right, but the reactive component in base is going to be this proton. And so if we're ever asked, right, rank in order of reactivity, and we're doing this, reactivity study in a basic solution, right, the first thing to react is going to be those protons, without a doubt, right, without a doubt. Again, pKa of 5 here, pKa of 15. So the acid is more, acidic than the amide, but this is still appreciably acidic, right? 15, that's like challenging the acid chloride enolate. That's also about 15. Although I would say the amide is slightly more analyzable, or not analyzable, but slightly more, acidic here than the chloride is here, right? Because if you think about the resonance forms, it's a C minus O minus versus N minus O minus, right? N minus O minus is way better than C minus O minus, but that's just my opinion. You should ask Nasiri, I think, for her true opinion on the topic. But yeah, so we can say here, okay, this is clearly going to react here, right? This is clearly going to react here, and react here, right? At those positions, right, this makes sense. And we can even say, okay, if we're reacting on the carboxylic acid, specifically at the carbonyl, like it's probably equal to an ester, about equal to an ester, I would say. Right, that's how most people put it too. The other amines, like the primary and the secondary and the primary amine, right? Same sort of idea. But you have to always keep in mind that we're not going to always react at those centers, right? Especially in a basic media, which is what a lot of these reactions are going to take place in. These are the protons that are getting lifted first. Okay, so general reactivity, yes, it does go this way, but think about, right? Think about that. Think about the fact that the proton wants to be taken off first. Another kind of mind trippy thing here is that if I wanted to put the ketone and aldehyde here, they're actually going to go here for our class. Okay, and so you might be wondering, well, wait a minute, didn't we say that, you know, these guys are more analyzable than an anhydride? Yeah, that is true, right? That we did do that, put that there. But the reason why we're putting these here is if you think about these derivatives here, right? So let's focus only on the derivatives right now, right? The acyl halide and the anhydride are super reactive, super reactive. I mentioned before they have fairly acidic leaving groups, right? That makes them way more pretty reactive. Okay, we're going to come to see that these guys here can react in conditions that require no catalyst. They just kind of react with everything. On the other hand, esters and amides, which had the fairly basic leaving groups, they need some kind of catalyst to react because they need help pulling off those leaving groups, right? And if you remember back in 118b, we also needed catalysts for ketones and aldehydes. So in terms of carbonyl reactivity, right, we have to say that the aldehyde is less reactive than the anhydride and the ketone is less reactive than the aldehyde, right? We're going to put in this order here. And again, it's just for the sake of trends that we're learning in this class. Okay, so that's why I like drawing, these trends on 2 different pages. It's because they're a little bit different from each other, just a little bit different. Okay, but I want you guys to understand the basic idea here, right? What it is that we're looking for when we think about reactivity. Now, for those of you that are a little more advanced, and you can skip this if you don't want to hear this, it's not a big deal. But it turns out that actually the aldehyde is more reactive than the anhydride. And this order here that I'm showing you now fits all the trends that we saw on the last page, including the reactivity trend we see on this page. So this is actually the true ordering of all the acyl molecules. But it's a little complicated to put the aldehyde here, right? It's a mind bender, right? The fact that the anhydride is more reactive and more analyzable than a ketone, it's a little hard to think about. So that's why we kind of just put this here, and then we just remind ourselves of this trend over here, or of these trends over here. Okay. I guess I also should have mentioned the CY and CX, the CY and the CO bond thing. The CO trend works. Okay, so pink line trend here works here. The red line one is not a very good one. I'm not really convinced that it makes sense on these ones, although I guess you could try it, like you could accept it. It's not that big of a deal. I think if you had to choose, you could do it, right? It would work. And then leaving group ability, again, doesn't make sense at all. Okay, but yeah, those are the trends, right? Those are the trends that we see and we expect. And all that information we just pull out of just looking at structure, mainly just resonance. So, when you're studying and you're, trying to figure out how do I memorize this? How do I internalize this? Internalize resonance, because resonance is what explains all of this, explains every single trend. Technically, even the leaving group ability, I guess that's a little more easier because you just think about which one's a better leaving group, but everything else, we just use resonance to explain it. Okay. So let's go ahead and, now that we understand a little bit about the structure, let's go ahead and get into the actual meat and bones of the reactions. And we'll start with the acyl halide. Okay, the most reactive derivative, acyl halide. Okay. Now, here's what I'm going to do for every single one of these guys. If there is a reaction that I feel like is generalizable, I will show its mechanism once, and then I'll show the reactions for everything else, because I don't want to keep writing the same thing over and over again. So for example, I will be showing the water reaction with an acyl halide. And if there's any other reaction similar to it, I'm just not going to draw out the mechanism, but I'll let you guys know. Okay, so we're always going to examine the water reaction with every derivative, because when we use water, you'll see what it forms. But acyl halides, again, so reactive, water is just going to attack. And what we get is this tetrahedral intermediate. Now, keep in mind, the chloride is such a good leaving group and O minus really wants to form that carbonyl again, that there is like no time wasted between attack and reformation of the carbonyl. Like it's just going to instantly collapse this intermediate, this tetrahedral intermediate to form the carbonyl once again, because Cl minus is such a good leaving group. And so what we're going to get here is a really badly protonated carboxylic acid. Remember from chapter 19 how we said that it should never go there? Well, the fact that it's there should to tell you how acidic that is. And chlorine will pick up a proton, right? Show the actual movement. Don't be late. Actually, you know what? I should just take my own advice. Let me just show it. There we go. And what we get is a carboxylic acid and HCl. Okay, so we're going to notice that anytime we use water or we do a hydrolysis of a derivative, so cutting with water, we're going to get back to the carboxylic acid. Okay, we're going to come back to the carboxylic acid. Now notice how there's HCl here. That's pretty bad. You don't want that. You make a lot of that because that can hurt you a lot. So what we use are specific compounds. One of them is pyridine, which looks like this. And the other is T, or triethylamine, which looks like this. Okay. What you'll notice about these is that these are amines with lone pairs. Oh, I guess that's pretty obvious, but these lone pairs are able to pick up protons. If you have pyridine or T, it's not going to be chlorine that picks up the proton. It's more likely that the amine picks up the proton. So I use pyridine for this one, so pyridine will pick it up. And what we get is a pyridinium salt. A little bit of my own experience in lab. Pyridine stinks. Like, actually, it doesn't stink, but there's something about pyridine that when you smell it, there's something bad about it. Like your body just knows it shouldn't be smelling it, and you'd have like a really bad, like you have a response to it. And so whenever there's like a leak of pyridine, or if there's I'm trying to pull off solvent off of my reaction and there was pyridine in it, you can really smell it if pyridine's like leaking through. It's such a strong smell. It makes me, a little dizzy. I'm not dizzy. I don't want to say I'm dizzy, but I really don't like the smell of it. Okay. And pyridinium salts are terrible. I've had the worst experience with them. Okay. Now the water reaction, right? If water can react and it gives us the acid, then acyl chloride should also be able to react with organic water or alcohols. And so the mechanism is exactly the same. Just replace OH2 with ROH. So you can just literally put R here like this, and the mechanism is exactly the same, right? Replace here with R. Let me do that instead. So you can replace it with this and this, right? Overall, then the reaction gives you an ester. And again, there's going to be HCl forming because we're going to leave it. So let's use T this time. I've never used T before, so I don't know if it smells bad. But I can only imagine it smells better than pyridine. We can also react acyl chlorides with carboxylic acids, and I will show this mechanism just because it's a little, it might be a little bit new. But remember, acids attack by delocalizing electrons. I'm already drawing it because that's how quick it is. It adds on and it immediately kicks it off. That's how much it hates it. Okay. Or I guess it's not much it hates it, but that's how stable that leaving group is. It's just gonna instantly leave. And then T will pick this up. And we get an anhydride. Very last reaction for things that we should be familiar with. It's going to be the acyl halide and an amine. And so remember how we were using pyridine and T, which are amine compounds to pick up protons. If you use an excess or at least 2 equivalents of this amine, you don't actually have to worry about using pyridine or T because the excess amine will pick up the protons. You can imagine that this reaction here is the same as this one, all you're doing now is replacing this with NH3. Okay, so again, how the mechanism would look, right? Just to help you guys out a little bit on that. And help myself, because I don't want to, in the past when I've made this video, I would get hand cramps very early on because of how much I was writing the same thing over and over again. Okay. Now, one thing I do want to make very clear is that primary and secondary amines also react. So this was ammonia, but primary and secondary amines also react. And you'll notice that when they do, it's almost as if we're losing hydrogens. Right, this has 2, this has 1, this has 0, and this is ammonia primary, secondary. And you might be wondering, right, like what is the reaction with the tertiary amine? Another great question is, well, we're using a tertiary amine to act as a base. Why doesn't that tertiary amine react too? Well, if we imagine that a reaction, right, where let's say we have acyl chloride and it reacts with triethylamine, right, what we're going to get as a substitution is this here. And this thing here that looks very awfully like a squid is very, very, reactive. It really wants to get rid of that positive charge. Now, again, if we kind of look at the reaction here where I modified it, what happens is the amine adds on, chlorine pops off, and then a proton is taken off of the group, right, off the amine here. What would we take off of this nitrogen, right? What would we take off of this squid to get rid of that formal charge? The thing is, we can't take off anything. This tertiary amine has no proton. So it's actually going to decompose, or it's going to fall apart, because this amine cannot, right, give a proton to get rid of that positive charge. So tertiary amines, or amines with no NH bond, are bad nucleophiles, but they're good bases, because if they're bad nucleophiles, then they can focus all of their electron energy into just being a base and picking up protons. So that's why we see tertiary amines used a lot as weak bases. Okay. One little thought occurred to me, because this looks like a squid to me, but imagine you open a tin can. You're in the games and you open a tin can, and on your targona you see this squid, and you have the little needle up here. I think I would be very upset. I think I would realize that, oh man, I won, track star, I won the red light, green light, and then now I lost here. I'd be pretty sad. Okay. This is something that reminded me of. Cool. So these are just the reactions of acyl halides with common nucleophiles, right? And you'll notice again, acyl halides kind of make all the derivatives, right? We can make esters, anhydrides, amides, right? We can make carboxylic acid. All of them can, but a point to be said there. Okay. So what other reactions can we do with the acyl halide? Well, we can reduce acyl halides, right? So reductions is also something we are capable of. And remember, our most powerful reducer is going to be lithium aluminum hydride. Okay, so let's kind of understand how the lithium aluminum hydride reaction works. Now, if you remember back to ketones and aldehydes, it was essentially very simple, right? The aldehyde just attacked the carbonyl. The lithium hydride attacked the carbonyl. And the same thing's going to happen here, right? Hydride is just going to attack the carbonyl. You might remember with the carboxylic acid, right? First thing we did was we attacked this proton here. Well, that proton no longer exists in the acyl halide, so we don't have to worry about that anymore. We can go straight to the carbonyl here. Now, once again, right, acyl halide, this is going to come down, kick off the chlorine. But what do we get? Right, we get a aldehyde. So we get an aldehyde after we remove or we add one hydrogen onto the acyl chloride. Now keep in mind, the lithium aluminum hydride, let's say this was at a 1 EQ, so we only had 1 mole of lithium aluminum hydride for every 1 mole of acyl anhydride, or sorry, acyl halide, we still have, right? So we used 1 hydride, but we still have 3 of them, right? We still have 3 more on the species here. So what do we think those other 3 hydrides are going to do? Just going to hang out? Just going to like not do anything? Well, this is an aldehyde, and the hydride can also react on the aldehyde. Right? Aldehydes are also reactive to the aluminum hydride, and so we can get a complete reduction after aqueous workup. What do we get other than a primary alcohol? Okay, so lithium hydride, we're going to see this trend with all the derivatives, really. So spoiler alert already, but we're always going to see a complete reduction. We tried to limit this reaction to 1 EQ, but there's still more hydride, right? 4 hydride to 1 reagent. So all 4 can react, and we only need 1 to reduce the acyl halide, and we just need another to reduce the aldehyde. So very, very hard to control this reaction. Expect complete reduction if you use it. So how might we stop this reaction? Well, what if we just, again, use the 1 EQ limit, and we reduced the number of hydrides on lithium aluminum hydride? So essentially, what if we just turned lithium aluminum hydride into something that had 3 R groups and 1 hydrogen? This here is known as LIPA, lithium tritert-butoxy aluminum hydride. Okay, so that's the name. And it functions exactly the same as lithium aluminum hydride. It's exactly the same. It just only has 1 of these hydrides. Okay, so 1 hydride, so it only reacts once. Comes down, kicks this chlorine off. And what we get is the aldehyde here. Now, a very good question to ask yourself is, sure, there is only 1 equivalent, but what if there was an acyl halide and an aldehyde really close to each other? Who do we think the next equivalent of LIPA is going to react with? So let's say there's another LIPA hanging out nearby. Who is this LIPA going to attack? Okay, remember, there's only 1 equivalent, so it has to, react with something. But who is it going to react with? Who is more electrophilic? You can quickly come back here, but who do we say was more electrophilic? The answer is the acyl halide. Aldehyde, we're going to say, is less electrophilic than acyl halide. And so, because of that, we're not going to get the attack here. We're going to get the attack over here. And so we're always making aldehydes. So this is how we can stop the reaction. Okay, this is how we chemoselectively force all the acyl halide to react and hopefully none of the aldehyde. Now, don't get me wrong, it's not like LIPA can't reduce aldehydes, but if we limit it, we can prevent it from overreacting with the aldehydes and secure a lot of aldehyde. So this is how we get aldehydes from acyl halides. You can extend the same type of reaction to Grignard, right? Same sort of logic where we say, hey, Grignard can attack the acyl halide, and what we get is this here. It doesn't matter if we use RLI or MGBR, and what we get is the ketone. And a couple of you might think, oh, we can just do 1 EQ here, right? 1 EQ would work. Well, it turns out Grignards are a little more crazy because they're more basic, and especially with the MGBR variant, and actually probably even the lithium variant, because I think the lithium variant is more basic, and the MGBR is more nucleophilic. But these guys are a little less discriminatory in their attack. R- is actually, as much as it would probably react more with the acyl halide, it can also very much react with the ketone. And so it turns out, if we try to limit this reaction, let's say at 1 EQ, you're actually going to get some attack also on the ketone as well, which gives us the tertiary alcohol right after workup. And so let's say, again, we did a 1Q limitation. It turns out 1EQ gives you a mixture of tertiary alcohol and of ketone. So 1EQ is actually a pretty terrible reaction to do with Grignard, because if you did limit it, it might work, but it also might not work. It's not very, it doesn't really make sense to limit this one. So we tend to do, again, a complete reduction here so that we can prevent a mixture of ketone and alcohol. And we purposely go all the way to the tertiary symmetrical alcohol. Symmetrical because the R groups are exactly the same. So again, another complete reduction. How can we prevent this? Well, look, turns out the acyl halide does have a way of preventing the attack, and that is to use the Gilman. Because remember, acyl halides are so electrophilic that most nucleophiles will react with them. Okay, and so what's going to happen here is one of the R groups will attack. And we form a ketone here. But think back to 118B. Did Gilmans react with ketones? No, not at all. Gilmans don't react with ketones. So we're actually going to be able to stop here, because although Gilmans can react with the electrophilic acyl halide, can't really react here. So another place where chemoselectivity is being exploited, because this will, the next equivalent of CuLi can react with the acyl halide, right? It won't react with the ketone. Okay, so acyl halides, this is actually going to be really important. We can actually stop acyl halides in their reductions, which is not something that we can say about most derivatives. Okay, so it's a little bit unique to the acyl halide. Okay, cool. Now, one last thing, I actually did forget about this, but just a little bit of a reminder of how to make acyl halides. SOCl2, right, or PBr3 to make the bromine variant. So just a reminder of how we made these guys in the first place. And remember, we typically use pyridine, although you don't have to, right? But you could. I would recommend it. Okay, cool. I know the chlorine variant is like the one that everyone's comfortable with, and I am, but don't forget the bromine variant also exists as well. I also want you guys to notice how we used a lot of neutral nucleophiles, right? No catalyst. And again, that is all about how reactive that leaving group is, or how the reactive the acyl halide is in general. So neutral nucleophiles will do the job. Don't use catalysts for these reactions. It doesn't really make sense to do that. So I would really recommend not putting those on, like on an exam or something. You can just use a neutral nucleophile. Okay. We will see derivatives where we have to use catalysts because they're fairly basic and not fairly acidic. But we will get to that point when we do. So now that we've talked about the acyl halide reactions, oh, I guess I should include this just in case. There was actually over this, not over the summer, but kind of over the summer. This past summer, she really cared that they put all the salts that could form here. This is going to be either MgBr plus MgBr plus or Li plus. It really depends on which one you get. So just be mindful of that. All right. So now we talked about the acyl halide, we can talk about the anhydride. And if you think about the anhydride, a good way to describe it is that it's just a safer acyl chloride. Okay. Its preparation is a little bit different, right? But there are several ways to make it. Well, there's like 2 ways to make it, really. One way is to heat 2 carboxylic acids together, right? But remember that this only works for symmetrical, right? Or it only works for, symmetrical anhydrides. If we try to mix it up a little bit, like let's say that I try to do both of these guys, not only will we get the 2 symmetricals, but we'll also get the mix So this reaction fails if you try to do it. It's really, really bad. Don't ever try to do two acids together in heat. You're not going to get the one product you intend to make. We can also bypass this by just going through the acyl halide, which again, we mentioned a lot in chapter 19, but it's a great bypass to do if you have to. And this is actually where we can make the mix in high efficiency, right? Because we purposely prepare one side of the anhydride to be the electrophile, the other side to be the nucleophile, and we get exactly the mix that we want. So, we have two ways to make anhydrides if we have to. Both are acceptable. But what we'll notice is that the anhydride really just has the same reactions as the acyl halide. There's really no difference. Like the water reaction, I think really what makes the acyl anhydride a little more difficult, I suppose, is just the fact that, there's a whole acyl group, right, that's part of the leaving group. But again, so reactive, right? It reacts pretty much similarly the same. This carboxylic acid will just pull off that proton there. And what we get is a carboxylic acid here. But don't forget, that leaving group is also organic. And so we have to include it in our answers. So when she asks for all organic products, keep in mind that the leaving group also counts. So always be paying attention to that, looking out for that so you know that you're not forgetting it. You can do the exact same reaction with ROH. And again, following the same procedure, just instead of OH2, we have ROH. What we should get is an ester and carboxylic acid leaving group. So that's also a product. We can also take an amine and make amides. Everything still applies, right? Primary, secondary, and ammonia can all react, but not tertiary. And once again, don't forget that carboxylic acid leaving group. Okay, so far, all the reactions have been pretty much exactly the same. Because again, anhydride is chemically equivalent in a sense to the acyl halide. It's really just a safer one because you don't have to worry about the pyridine thing, right? Using pyridine to neutralize that bad acid. Carboxylate salts are pretty good. Oh, that actually is a very important thing to realize because remember, amines, back in chapter 19, we talked about how amines deprotonate carboxylic acids. So if there is an excess, let's say an excess of amine, which is possible, we're actually going to get a carboxylic salt. So look out for that. That could be a really good question for her to ask, is to do something like that. Although that would be a little cruel, but it's something to always keep in mind. Keep your brain, thinking about those kinds of things. Now, the anhydride also brings us to the beginning of cyclic compounds, right? So you might remember this also back from the 118, the chapter 19. The fact that cyclic molecules can now exist for the derivatives, and so don't freak out too much with these guys. Just remember that, like, let's say we have some nucleophile reacting. The general formula for any sort of ring breakage. So actually, let's write that. So let's say I have a Y derivative reacting with an X nucleophile. The general formula is the following. Okay, where Y tends to get protonated at the end. Okay, so if we were to take this general formula and apply it to, I don't know, let's say an amine, essentially what we're saying then is that if the O is the X group or the Y group here, or really not the O, but this whole carbonyl group is the Y group, then that should be down here, typically protonated. And then the X nucleophile or amine should be over here. And this is actually the answer. Okay, so don't be afraid. Essentially, all we're doing is we're cutting this bond here. So this is another way to visualize it. We're cutting that bond there. And give yourself a lot of space. Okay, put the nucleophile on that carbonyl from where we cut that off, and the leaving group just pronate it. And there you go. That's typically what we're going to get. Although again, if there's an excess of amine in this reaction, this is going to be a carboxylate salt. So keep a watch out for that. Cool. So those are the nucleophile reactions. And again, introduction of the cyclic compounds with the anhydrides. Acyl halides can't really have cyclic compounds because that would mean 2 bonds on chlorine, which is bad. That's really bad. This guy is not really happy at all. Again, reductions exist for the acyl anhydride, and they're going to be the exact same that we saw on the last page. Okay. Now, I do want to go through the lithium aluminum hydride for one here, just to sort of highlight something interesting here. So again, kick off. Let's go ahead and kick off this acetate group here, or this carboxylate group to get to the aldehyde. And we have a carboxylate. Okay. And remember, lithium aluminum hydride, which still has 3 hydrides on it, who's it going to reduce, right? Who's it going to attack? It's going to attack carboxylate, or is it going to attack the anhydride? Or sorry, the aldehyde. Clearly going to attack the aldehyde, right? That's the more electrophilic guy. And what we get is a primary alcohol. But wait a minute, right? We still have 2 equivalents on that lithium hydride. So remember, we're doing that 1EQ reaction. And notice how 1 equivalent reduces the anhydride, 1 equivalent reduces the aldehyde. We still have 2 more. 1 equivalent is actually going to reduce the carboxylate. So remember carboxylate reductions, we're also going to do that. So a little bit of a mind bender here. Okay, and so just keep in mind, right, how we did this reaction in the past, right, but we're going to kick off. I guess it's better to draw this as a bond so it doesn't get too confusing. We're going to kick off this oxygen here. And when we get down to here is the aldehyde, and look at that, we still have 1 more hydride here. That hydride can reduce this aldehyde to get to here. Now you might be wondering why I walked you guys through that whole thing, right? You might be wondering like, why did I even bother with that? Because I want you to realize that when we do the workup here, we're not only working up this primary alcohol from the left side of the anhydride, we're also protonating the alcohol from the right side of the anhydride. So essentially, we're going to get 2 alcohols here. Now, this might not be such a big deal for symmetrical anhydrides, but imagine if we had this anhydride that we made earlier. Lithium aluminum hydride is not going to just afford you the alcohol that you might think it affords. So a good rule of thumb is it's going to give us this guy here, right? That's the guy, that's the alcohol we're going to get. But we're also going to get this alcohol here. Okay, we're going to get that alcohol there. And it's important to realize that we're going to get 2 different alcohols from this reduction because we can reduce not only the anhydride, but also the carboxylate that results. We saw that, right? We saw how that could work. Okay, so anhydrides are a little tricky like that. Again, anhydrides, if we react them with LITBA, the point just becomes, hey, when we get to that aldehyde, right, I want the mechanism exactly the same, right, as this up here. But when we get to the aldehyde, who is more reactive, anhydride or aldehyde, right? Who do we say is more reactive? And we said anhydride is going to be more reactive. and therefore reduction is stopped here. Okay, so we get complete reduction here. But we get selective controlled reduction with LITBA. And that's what, that's the point of having LITBA. Otherwise, we wouldn't really need it. You can imagine then that RMGBr is going to give you, especially in excess, right? We're going to do this reaction in excess. Typically, when you use an organometallic like RMGBr or RLI, it's going to be in excess. There's no real use of limiting it. Although actually there is one use, and I'll show you guys towards the end what that one use is. But in general, it's going to be used in excess. And what we're going to get is not only, let me try it this way. This symmetrical alcohol, but we're going to get two of them, right? Because again, we're getting one from this side and one from this side, right? And excess is going to reduce everything possible, right? So we're going to get two of these alcohols. Now, the interesting thing is that, again, anhydrides being equivalent to acyl halides can also react with Gilmans. So we do have the ability to make ketones here. Okay, and as far as I know, Gilmans cannot react with carboxylates. They're too weak. And so this is going to be the one reduction that we do where we actually get a carboxylic acid leaving group. Okay, the reason why it's an acid form is because I did an acid workup at the end. Okay, if that was not there, it would be the O minus, right? The O minus. So to my knowledge, Gilmans are just not strong enough to destroy carbonyls, right? Not strong enough to destroy carboxylic acids, which is what we saw, otherwise we would have saw it in chapter 19 that a Gilman reacts with carboxylic acid. It doesn't. So we're not going to reduce this also. But in every other reduction, RLI, LITBA, lithium anhydride, we do reduce it. Okay, and that's the anhydride. Again, so it's carbon copy of the acyl halide. Now again, as we noticed with the last guy, right? Neutral nucleophiles, no need for a catalyst. Leaving group is just that reactive, right? But as we move on now, we're going to see that our leaving groups are not very good, right? If we go back here, -5 to 5, fairly acidic, but 15 and 35, these guys are very, very, very basic. And so because of that, we're going to have to move towards, we're moving towards less reactive derivatives. We're going to need more, powerful reagents. And so this is sort of our introduction to the ester. Now, the ester is a kind of an interesting person because we've actually learned a lot about the ester even before we got to 118C. For example, you guys learned that if I had, let's say, a bromide here, I could react it with a carboxylate anion. And this SN2 reaction, remember SN2 has inversion, so a reminder on that, but this SN2 made a ester. I could do the same reaction with bromine, but use an SN1 substrate, where SN1 racemizes, so this is racemic. We make the same ester. Okay, so SN2 is stereospecific, SN1 is not stereospecific, but it's how we make an ester. Okay, you guys also learned back in 118B that, hey, if I wanted a ester from a ketone, I could use MCPDA. And what that does is it inserts an oxygen in between the carbonyl and a carbon. Now here we have a secondary carbon and tertiary carbon. How did it goes to tertiary? That is migratory aptitude, which is defined as such. This is very rough. If you want a more specific migratory aptitude, just look in your 118B notes for chapter 17, I believe, chapter 17. Okay, that should work. Now, carboxylic acids, right? We learned very quickly that, ROH, H+, Fischer esterification gives us an ester. Just keep in mind that RO- right? ROH doesn't work, right? This just gives us the carboxylate salt because of that annoying acid base that can occur. Okay, so keep in mind that it's only this way that makes the ester, not this way. So I'm going to go ahead and get rid of it. But if you have to, go back and rewrite that in your notes if you have to. Anhydrides and acyl halides, right? They both can also make, these guys can also make esters. This is just introducing alcohol to them. Just keep in mind that we need pyridine with acyl halide. And so we'll make an ester from either of them with that neutral nucleophile. There's also one more very niche carboxylic acid reaction with diazomethane, which you guys might remember. And so to kind of show you how this reaction works, recall that diazomethane is basically this compound here, N2 with this on a CH2. And remember, CH2 minus is super basic. That carbon is going to pull off this proton here to make the carboxylate. And at the same time, right, what we form is CH3N2. Now, N2 is like the best leaving group known to man. So when this carboxylate forms, it like immediately SN2s this protonated diazomethane. And what we get is specifically a methyl ester from that diazomethane. So if we want to specifically make a methyl ester, we could do so. With diazomethane. Do not try to make any other type of ester with this. It's not going to work. Okay, it's methyl ester specifically that is going to do this reaction. Okay, so quite a few ways to make esters. They kind of a interesting little fella that we have available to us. So let's look at the reactions of the ester. And again, I want you to keep in mind that we're moving on to a more basic leaving group. So we're going to need acid-base catalysis. Okay, so we need catalysis now. And so when we look at the water reaction, we're going to first examine this reaction in acid, and then we'll look at it in base. As such, acid-base reactions are reversible, so reversible arrows are going to be needed. So remember, whenever we have acid, there's a proton, something's going to get protonated. Essentially, the ester is going to act as a base here. So how did it act as a base, or how do we, determine basicity, right? We looked at these resonance forms here, and we said, hey, there is an O- on the carbonyls, oxygens, so that's where it's going to get protonated. So very first thing is to protonate the ester. And protonated ester is a lot more electrophilic than neutral ester. That's what we saw with ketones and aldehydes as well, also the carboxylic acid. So water, who was probably just hanging out, because there was nothing to attack, now that there's a protonated ester, we're going to attack the carbonyl. And what we get is the following intermediate. Now in the past, O could return back to a carbonyl because there was such a good leaving group, but there really isn't any good leaving group here other than water. But if water leaves, then we just go backwards, right? If water added on and it leaves, we accomplish nothing. We really want to kick off OR here, but kicking off OR minus here is that's a basic entity, acidic media. That basic entity is going to destroy our media. So what we're going to do instead is we're going to prepare OR into a better leaving group. How do we do that? I'm going to do something, it's a lot more abbreviated, but you should draw it out in full. You should draw a nucleophile, a base, picking up that proton, like water, or water would work, pick up that proton. And then have the OR, gain it back, right? So water gives up a proton, and then the OR takes it. Just be a little more, better with how you write everything out. I'm just being lazy because I can, right? But now OH can come down and kick off OR plus or ROH plus, which is way better leaving group than RO minus in acidic conditions. And when we end up is with a protonated protonated carboxylic acid here, anything can really pick up that proton, but something will, whether it's water or alcohol. And what we end up with is going to be a carboxylic acid with alcohol. And just like with anhydrides, alcohols are also organic, so include that in your answers. So acidic media hopefully makes a bunch of sense. It's just proton transfers to make better groups and, you know, eventual hydrolysis of the substrate. Well, basic is a little more interesting in that, again, no protons because it's basic, but we have strong nucleophiles. So eventually RO minus will attack. And what we get is OR, oh, sorry, not RO minus, my bad. This would be OH minus. We will see RO minus attack soon. Apologize for all these tiny little mistakes. It's pretty late, but I wanted to make this soon. Anyways, O minus can, right? O minus wants to come down, but notice how there's OR minus and there's OH, right? If we kick off OH, that's just making the same OH, so we're going backwards. And if we kick out the OR minus, right, that's making a basic nucleophile. So a really good question is like, what do we do, right? There's no way to protonate this. There's no way to make OR like a better leaving group. So what do we do? Turns out that we are going to go ahead and kick off OR minus to form the carboxylic acid. But when this OR minus forms, right, it immediately picks up the carboxylic acid proton. So even though OR minus is like a very basic entity to begin with, right, and it's not the best leaving group, when it leaves, it has the ability to stabilize itself by picking up the carboxylic proton. So it's an okay thing to do actually in this case. And we will see this in the future as well, where we kick off a bad leaving group only to stabilize that leaving group immediately, right? We will see this for midterm 3 or the final, I guess it's the final now. And so notice how both the acid condition and the base condition make alcohol, but you know, it's not protonated or deprotonated. It's just the normal alcohol. I think if you think about it, it might seem intuitive to think that it's going to be RO minus, right? But it's actually going to be ROH. Now we could protonate, we could do acid workup to get the carboxylic acid if we wanted to, but just keep in mind the direct result of the basic hydrolysis is going to be a carboxylate. Okay, that's going to be the direct result. So this is how we catalyze acid-base reaction of an ester with water, right? And as always, we get the result of a carboxylic acid. And we're going to kind of see the same thing in the amine, or in the amide, sorry, because again, amines are even more basic than esters. So we're going to see something quite similar in our reactions with that. Now, the ester, being one of the less reactive derivatives, right, doesn't have like a huge bulk of reactions with common nucleophiles. Actually, one thing hopefully you start to realize was that, you know, acyl halide being the most reactive derivative, we can kind of make everything from the acyl halide, right? All these derivatives were accessible from the acyl halide. And then if there is a primary amide, we could make the nitrile. Oh, the nitrile would go here, by the way. It's the least reactive derivative. So it would go right here. And then the anhydride can make these guys, right? The ester can only really make the amide, right? And we'll actually see that esters can make other esters as well. But notice how we can never go up. So we're always going down this reactivity ladder, but we can never go up. The reason for that is that going up would require us to add on better leaving groups. And if we're adding on better leaving groups, those leaving groups are going to leave instead, right? So really all you can do is go down the reactivity ladder. You can never really step up the reactivity ladder. But don't worry, there is an easy hack, because remember, the carboxylic acid is accessible from all these derivatives, and the carboxylic acid can make everything. So if you ever have to move up the reactivity ladder, all you have to do is make the carboxylic acid and then turn it into whatever you want, right? Typically what that would mean is like, you know, amide to acid and then probably chloride into something else. But, you know, you kind of get the point here of what we would have to do, right, to go up. But to make it, you know, the easier reaction is just going down. Going up is going to require a little bit more work. Okay. So like I mentioned, esters do have one more reaction, and specifically use the ethyl acetate. I actually use ethyl acetate every day. I have a squirt bottle specifically for it. it is a very, very good, it's a very, very good, you know, cleaning agent, solvent. I noticed that a lot of things in lab, if I wanted to clean, I just use ethyl acetate. Very, very, you know, nice thing to have around. So it actually smells pretty fruity too. It smells really nice. I like it. Okay. But this is ethyl acetate, and let's say that I needed ethyl acetate, right? But all I had in lab was methyl acetate. How can I make ethyl acetate? Well, if I have ethanol and acid, I can make this work. Okay. Ethanol and base will also work too. So we'll look at the acid mechanism and the basic mechanism. Again, most of you guys can probably do this, right? It's the exact same as we saw before, but we're going to use the ester as a base. Okay. I guess I didn't do it this way last time, but you can also do it this way too if you'd like. Totally up to you how you want to do the mechanism. I think on the other page, I just did it from the, oh, I actually messed up my arrows. I apologize, but I guess I don't have to do this because I just did this here. But if you do the arrows like I did over here, it just forms this. And that's not bad, right? That's not bad at all to do. Really, it's just going to form the same thing. So don't worry. I apologize if I confuse anyone with my arrows. Everything still works the same. But remember, when we were here in the hydrolysis, right, and we said an acid, this couldn't come down because the only good leaving group was the nucleophile we just added. We're just going to do the exact same thing that we did before, right, to get a movement that we want. So what I mean is take the proton, give the ethanol, or so the methanol component a proton, and then use it as a leaving group, right? Look at that. Completely generalizable mechanism right there. That's great. It's great when we can do that. And what we get is ethyl acetate, right? Again, initially it'll be protonated, but something in solution will pick it up, right? And we end up with methanol as well. Okay, so luckily for me, I was able to make that ethyl acetate that I really, really needed to do stuff in lab with. Now, let's say I didn't have acid available, but I did have methoxide. This reaction still works. Okay, but again, remember, oh, made this an acid here. Just remember that when it comes to basic nucleophiles, they just kind of attack immediately. So we get this OR like this. Okay. Now here's where things get a little kind of crazy. Not really crazy, but you know, things get kind of like, what the heck is going on? Like, why did we just do that? But it turns out with ester, you know, with this ester reaction in base, O- can come down and actually kick off methoxide very easily. And there's really no stabilization step here. We just get O- here. We have to wait for an H+ wash to get the methanol. And the reason for this, why is it okay to kick off O-, is kind of the same as to why we can kick off the hydroxide back in 118B to make enones. This reaction type is known as an E1CB. And the whole point of it is that we kick off a conjugate base that's not very stable. One of the main reasons is because there's some, you know, resulting stability in the system. Another reason is just that, you know, the pKa of this solution is already around 15 because it's methoxide. Methoxide is really close to 15, so kicking it off is not that big of a deal. The point here is being that this basic reaction works and it's pretty short, so I wouldn't really worry about it too much. But it's a way we can make other esters. This process in general is known as a transesterification, right? Because we are switching out one ester. I like to call this an ester length, right? Because this is a methyl ester. It's a different ester length than an ethyl ester, which is, you know, so sometimes you'll see me say ester length, and that's what I'm talking about specifically is this part here. The OR part is what I mean when I say ester length. Okay, but we can make different ester lengths with this type of reaction. Now, again, we can also make amides from esters because we're going down the reactivity ladder. And typically this is done in acid. And so just keep in mind, right, keep in mind that when we're using acid, right, for this reaction, it might be tempting to immediately protonate the carbonyl. But remember, what's more basic, carbonyl or an amine with a lone pair? I'll give you pK values so you can, be the judge of be the judge yourself. The answer is the amine always picks it up because 9 is way more basic than -6. So the first part of this reaction actually is NH4 plus forming. But just keep in mind that, there's going to be a small equilibrium between the amine protonated and the carbonyl protonated. And when the carbonyl gets protonated, notice how the amine lone pair frees up. The ester kind of just gave the amine electrons. It's like, go free, have fun. And then the amine is like, hey, you know what? I'm just going to go ahead and invest it right back. So the second that the lone pair is back on the amine, kind of just gets put back into the system on the ester, and the attack occurs. Okay. Again, I'm going to be a little lazy here, but I'm going to just show the proton transfer in one step. Just keep in mind that you guys have to do it in 2. And what we can do here now is form the carbonyl and kick off oxygen, or ethanol there. And what we're going to get, again, initially is a protonated amide, but something in solution will pick up that proton. So I'm going to go ahead and erase it. Okay, but you guys should show something picking that up. Don't just erase it like I did. And that's how we get amides from esters. Okay, now again, you could use secondary, right? You can use primary and secondary amides. No big deal there. You'll just get your respective amide. For example, this one will give you NR2 like that. This one will give you NRH. Remember, tertiary amides, practically NR, because there's no proton. Remember, amines with no NH bond are bad nucleophiles, so they invest all their time and energy into being good bases. Okay, so don't use tertiary amines for nucleophilic purposes. Now, you might be thinking, yay, right? We have gone through all the nucleophile reactions, but there is another set of reactions that you should be aware of for the ester. And these reactions derive themselves from the ester enolate. So remember, LDA has a pK of 35. This proton here has a pK of 25. So we can actually pull off this proton pretty irreversibly with LDA. We can also do this reaction with the ester enolate a little more, less harsh with OR minus, where specifically OR minus it's going to be a very specific base. So while I'm drawing this, I want you guys to think about why it has to be very specific. So why is that with ethyl acetate? If I want to make the ester enolate, I have to use ethoxide, right? Why might I use ethoxide here? So think about that for a second. The answer lies on this page right here, right? Because what happens when I have a base, an RO minus, that is a different ester length than the ester that I have present? I get a transesterification reaction. So a good sign that you're doing an ester enolate reaction is if you see a alkoxide that is the same length as the ester that you have, right? The R group on the ester. And that's how you know you're making the ester enolate. Either one of these will work. This is more of an irreversible, removal. Like you will 100% take away all of your, really what I should draw is like this. You will 100% destroy all of your ester into enolate. You have to actually do this at a pretty low temperature if you want to prevent a self-condensation. So -78. This is actually, I might have mentioned in the past, -78 is actually a mixture of dry ice and acetone. That's why you see this very specific number. So if you're ever like looking at papers or you see this in your notes, that's where that numbers come from. It's the combination of dry ice and acetone. This one is a little more equilibrating because again, if this is a pK of 35 and this is 25, 10 units, pretty irreversible. 25 and 15 is a lot closer, so the reversibility is a lot more tighter. Right, the equilibrium is a lot more tight. And also notice how the alkoxide is actually more acidic than the enolate. So we're not going to get a complete deprotonation. But in general, you only need about like 1 to like the 1,000th. I think it's a good amount of deprotonation to get the reaction to work. Okay, so why is it that I'm telling you guys about the ester enolate, right? What's the importance of it? Ester enolate can act very nucleophilically, like we saw with the aldehyde and the ketone enolate. Really, you should just be familiar with the following, transformations. But if this is a nucleophile here, we can basically use, attack different electrophiles. So we can do SN2 reactions on alkyl bromides, right, or alkyl halides, really. So we can do, I'm going to draw it this way so you can see it really, right? We can transform about the alpha carbon as such. So imagine you have an ester and suddenly the length of the ester on the alpha carbon changes. That was an ester enolate attacking an alkyl halide. We can also attack epoxides. And so remember, the epoxide fragment, carbon, carbon, oxygen, carbon, carbon, oxygen, just like that. And just a little bit of reminder, right? Let's say we had an asymmetric epoxide. We're always attacking on the less sub side. So we can attack epoxides just like that. We can also attack like ketones and aldehydes. It's also possible. And what this will give us, right, is an aldol, but with an ester. And if you want to keep, right, the aldol specifically, you typically have to do it at a very low temperature to isolate that. But any sort of heating, and you can get conjugated esters. Okay, so return of the aldol. Although this is more, ester enolates are so useful and unique that we're actually going to see them again all the way in chapter 23, which is like final material. So we're just kind of broaching this is like the tip of the, not the tip, but like the top of the iceberg or tip of the iceberg, whatever you say, not an actual appreciation of the system as a whole. Okay, we can also, again, just to get you guys familiar with these reactions, we can attack, like, let's say Br2, and we can make this here, which you might remember is kind of synonymous to the HVZ reaction that we talk about. Okay, this reaction will work, and this actually has application at the end of the quarter. Really, when we talk about peptide synthesis, it's going to be important. We can also react this with an enone. So again, this one again is also a little more applicable towards the end, but if we attack on the beta carbon there, I just want to show you guys all transformations just in case. You never know what's going to be gained. But these 3 carbons here are what we add on, right, on an enone attack, and that's what we're going to see there. I'm trying to think if there's any other significant. Well, the point being is that forming an ester enolate means that it can attack pretty much most nucleophiles. Oh, here's one that many people don't recognize initially, but acyl halides. This is actually an interesting one because acyl halides are acylating units, and they will actually acylate even an ester enolate. If you think about it, we can attack here. And remember, when that O- forms, like what's immediately going to happen, right? Come down and kick off that Cl. And what we get is this product here. So we can actually acylate, enolates as well. Okay, I guess I can give this same sort of, this here is just a carbon oxygen fragment, right? Is here is a carbon oxygen double bond fragment. That's what makes this one significant. It's a double bond fragment, as opposed to this is a single bond fragment. And then we can reduce that, or we can dehydrate that down into an enone if we wanted to. But yeah, so anytime you form an ester enolate, just think like, hey, is there an electrophile? If there is, then react it, and you will probably get very close to the answer, if not the correct answer. Okay, so electrophiles are, they shiver in the shadow of an ester enolate. Now, keep in mind, ester enolates, these guys are less analyzable than ketones and aldehydes that we used before. And that shouldn't surprise you because, again, remember, it's this resonance form here that kind of does that, right? Aldehydes and ketones don't really have a resonance form, just like an acyl halide. So that's why these guys make really good enolates. Okay, I guess a little bit of an interesting thing here is like, you might think, oh, why are we using esters as enolates? It turns out if we try to use an acyl halide or an anhydride, okay, turns out acyl halides will actually decompose. What will happen is they'll eliminate themselves. Anhydrides do this as well. They eliminate themselves to make these really interesting structures known as ketenes. Ketenes themselves are very volatile, and actually two ketenes will add together on themselves like this. And so what will form is this here. So very volatile species, but we can actually form, I guess we can form esters, right? Cyclic esters from these molecules. Oh, speaking of cyclic esters, everything that I said about anhydrides also applies to esters and amides. So I apologize for forgetting about that. I'll make note of it, but esters, in the same way that anhydrides can react in cyclic form, same thing can happen with esters. So let's say, let's do a transesterification. Right, let's do a transesterification. What did we say? We said that we could break this bond here, right? Add the nucleophile and protonate that Y group that is left, and that's the correct answer, right? That is the correct answer there. Okay, we can do another one. I guess we can do an amine here, right? Amine and acid, same thing, right? We can cut this bond here, right? Protonate that Y group and add the nucleophile here. There you go. That is a correct answer. You can do the same thing with the amide, although we'll see that in a bit, what we could do with the amide, right? We haven't gotten there, but that was I realized I forgot for the ester, so I apologize. Okay, cool. So those are the ester reactions with common nucleophiles, and ester reactions also as a nucleophile on electrophiles. Okay, so keep that in mind. Alpha transformations, right? So alpha transformations can be accomplished with the ester. Now, all that really leaves us is with the reductions. Okay, and so again, if we have an ester and we use lithium aluminum hydride, how is this going to reduce? Always, 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 there's going to be an attack. And this is where things get a little bit interesting. Okay, it turns out that lithium aluminum hydride on an ester is very similar to lithium aluminum hydride with a carboxylic acid, in that when we form this intermediate here, okay, the O- will actually come down and kick off OR- to form the aldehyde. So you might remember with the carboxylic acid, we kind of did the same thing, right? Except here we had like AlH2 or H3, right? O- came down and it kicked off O-. Same thing here. It's going to kick off O-, right? If you think about it this way, lithium hydride is it's a very basic entity, right? OR- is less basic than that, so it's okay to be kicking off OR-. Okay, you actually kind of learn that some groups that we consider bad leaving groups are not actually as terrible as we move on But anyways, it's kind of similar in that way, right? In that respect, that O minus kicks off another O minus. And we get the aldehyde. Again, we still have 3 equivalents of hydride. Okay, so even if every single ester reacted, right, there's still going to be ALH3s out there in the world, right, in this tiny, tiny glass. And we're going to get, again, complete reduction. So don't be surprised that we can completely reduce with aluminum hydride. It is like a super reducer. It destroys everything. So how do we limit this? Well, let's try the LIPA process, right? Which was, I can use LIPA, which only has 1 hydride, but it reacts just like lithium aluminum hydride. And I get here and I kick off OR minus, right? And I get to the aldehyde. Now again, just to make sure we're doing things correctly, let's ask ourselves the question. When LIPA, right, at 1 EQ, so both of these, even this one was at 1 EQ, right? When LIPA is at 1 EQ, right, at 1 EQ, what will the other equivalent do? Will it react with ester or will it react with aldehyde? So who will LIPA react with? Let's go back here. Right, who is more reactive? Wait a minute. Aldehyde is more reactive than ester. Wait, that's weird. Because if aldehyde's more reactive than ester, that means that the next reaction is not going to be with the ester. It's going to be with the aldehyde. But wait, that means that I'm going to make primary alcohol, but I don't want a complete reduction. So LIPA actually poses a little bit of a problem because as a nucleophilic reducer, it's just looking to reduce anything that's electrophilic, and aldehydes are always more electrophilic than esters. So we actually cannot use LIPA on an ester or even an amide for that reason then. What we have to use is something known as dibble H. And so dibble H is an alane. You'll notice there's no lithium. It's basically an aluminum with 2 isopropyl, so diisopropyl, or I guess diisobutyl aluminum hydride. And the way that alane works is actually very similar to how borane works. So do you guys remember how borane works? You might remember borane was an electrophilic reducing agent, meaning that the derivative attacked borane. Okay, derivative attacked borane before it was reduced. Okay, before it acted as a reducing agent. So what's contingent on dibble working is that the carbonyl attacks the aluminum first, just like with borane, like it attacks the borane first. So I'm not going to draw the whole process because it's going to confuse you guys. But essentially, we have to get to this part. And then the hydride will work. It turns out the only way to get this reaction to work is to initially, in a sense, protonate the carbonyl. I did air quotes, by the way, protonate the carbonyl with dibble, and then allow it to to reduce. So the fact that that interaction is required first, the acid base between the carbonyl and dibble, means that only electron-rich carbonyls will react. Okay, and so I will just draw the dibble reaction the way that you would probably expect it, right, on an exam or something. But what we're going to see is something like this. Okay, where O minus will come down and kick off OR. And what we get is an aldehyde. Okay, and again, who is more electron rich, who is more basic and willing to pick up dibble? It's going to be not the aldehyde, it's going to be the ester. And so the esters are what get selectively reduced by dibble. So it's like a clever little trick, right? Using a different type of reducing agent to make sure that only esters are reduced. Now, in reality, right, Dibble actually never has to make a choice. Okay, and I'll explain what I mean by that. Right? Why is it that Dibble doesn't have to make a choice? It's because if I draw what really should be happening, so when we get here, the hydride attacks here, what we get is this. It turns out that this intermediate here that I'm about to draw is actually a stable intermediate. Okay, it's a pretty stable intermediate. And so it's not until hydrolysis, so not until we add H plus H2O, that this will collapse into the aldehyde. Okay, so it's a little bit different from what you guys are used to seeing, right? And it's not like anything else on this page, which might be why in this series might not have shown you guys a mechanism for it. But I guess you could maybe use this one too if you wanted to. You could say that this comes down and kicks off this guy. But in reality, it turns out that this here is stable, and it's not until hydrolysis that it collapses into the aldehyde. So in reality, Dibble never actually has to make the decision between an ester and an aldehyde, but we will say that for the sake of the course so that it mimics everything else that you've kind of learned in this class. Okay, I know that's not like the best way to do things, but it's the way that we're going to have to, unfortunately. Okay, I realize actually we can still copy my mechanism, and I like my mechanism, so let's do that. So let's actually, because I realized that we can still use this. All we have to do is this here, and we pretty much get, you know, where I was trying to get at initially. Okay, so I'm actually, what I'm going to do is I'm going to write my mechanism down here. How I would write it, at least, because I really want to show that it's this interaction here that's causing, you know, the Dibble to be selectively reduced. Cool. So Dibble is going to work really well on amides because they're heavily electron rich, and they work pretty good on esters. Okay, that's why we're using it on esters and not LIPA. It turns out though that BH3, right? I mentioned BH3 earlier. It turns out that BH3 is actually not that good for esters. So, I mean, I guess you could use it if you wanted to, but using BH3 gives you a complete reduction. It does not give you a selective reduction. So there's really no point. You can just use a lithium aluminum hydride. Okay. Now, esters can also react with organometallics like RLI, and the reaction is very standard. Where O- forms, kicks off OR, right? And what we get is a ketone. Well, now this one's not very hard because, again, if we're in an excess or even 1 EQ of RLI, ester is definitely going to, you know, or ketone is definitely going to react with the RLI instead of an ester. And so what we're going to get are symmetrical ketones once again. It turns out that esters cannot react with Gilman's, and that should make sense because remember back here, Gilman's reacted with acyl halides and anhydrides, but they did not react with ketone and aldehyde. So if they stop reacting here, that means that they won't react at the ester, neither will they react at the amide. Okay, so do not try this reaction. It will not work. But yeah, those are the reductions of an ester. And so with that, we come to the penultimate derivative, which is the amide. And one thing I'd like to say before we get started is I'm going to continue to use the dimethylamide. And at the end of this, we'll talk about why I didn't want to use this guy. Although actually we kind of did talk about it, but we'll discuss it a little more. Okay, but we're going to basically do our reactions with the amide here. And if we think about how to make amides, pretty much when X is equal to chlorine or it's an anhydride, right? We could just use an excess of some, amine, and we get the amide, and we kind of called it a day, right? If X equaled OR, right? All we needed was an H plus catalyst added in, and we would still get the amide. So really, we only know how to make amides in 2 ways, and not in very many other ways, but that's not too bad. Essentially, every derivative has access to the amide. So again, let's go back here. We look at the reactivity tree again, right? Quite a lot of slides. Every derivative has access to the amide, right? To form the amide. All of them can become the amide. So don't really ever feel like, that the amide is inaccessible. As long as you can form an ester, as long as you can form an anhydride or an acyl halide, or even a carboxylic acid for that matter, you have access to the amide. Okay, and so really with the amide, there's going to be one main reaction with the nucleophile, and that's going to be the hydrolysis with water. Just like with esters, it's going to be catalyzed because amides are the hardest derivative to react with. They are the most stable. They have the worst leaving group, and they have the most resonance with that, Y group. So let's go ahead and see what we have to do in acid to get this to work. Okay. So again, like we mentioned, H plus, carbonyl can take that. I know I haven't been doing many mechanisms with, that movement that I just did, but totally up to you how you want to do it, right? This is one way you can do it. So once we have that protonated, again, water, highly motivated now to react. And what we get is OH, OH2 plus, and with the 2 groups there. And again, in acid, things are a lot less complex, right? Because we can just do a proton transfer. Again, I will employ my lazy version. Please do not do this on an exam. But this will come down and kick off the nitrogen. What we'll get is a protonated carboxylic acid and an amine. You'll recall amines are highly basic, or not highly basic, but amines are pretty appreciably basic. And so amines will actually be what deprotonate the carboxylic acid here. Okay, so what does that leave us with? In acidic condition, we will have a carboxylic acid and NH4 plus, or any kind of, depending on, oh, sorry, not NH4 plus. This is going to be NH2 plus. Okay, amines are going to deprotonate the carboxylic acids, not water, because amines are more basic than water. So in acid condition, again, another organic group, make sure in acid condition, all of your amines are protonated. In acid, protonate amines, okay? Make sure that they're ammoniums. You want ammoniums, okay? Now, if we look at the basic mechanism, again, a little bit of highlighting what we talked about before in that, OH minus is highly motivated as a nucleophile. It doesn't need, any kind of acid. Well, there's no proton, so it's not like we could if we wanted to. But again, this one, really, really uncomfortable to do, but O minus has to come down and kick off NR2 minus. But just like with the ester, right, when it does do that, this N minus can pick up the proton off the carboxylic acid. And so in a sense, it stabilizes itself. But it's not a very nice thing to do. Okay. Notice in the basic media, the amine is not protonated and the carboxylic acid is deprotonated. Okay. So keep this in mind that this is what an basic condition looks like for an amide, and this is what an acid condition looks like for an amide hydrolysis. Okay, we could always protonate, right, do workup, but again, we get the carboxylic acid and we get NH2 plus. So don't forget that. We're going to get NH2 plus. And acid amines will be protonated. That's actually, when I took 118C, that's actually where I would lose my points on the predicted products and stuff, is because I would forget to protonate my amine. It's a very, very easy thing to forget. Okay. Now, once again, if we have, an amide, which is the weakest, or the least reactive derivative, there's not many nucleophiles that we can react this with, but we can do reductions. And why not do a reduction, right? Why not do it with lithium anhydride, right? The mother of reducing agents will literally destroy anything. So what we get is this here. Okay. Now, here's where things are a little bit interesting, because remember in the past when we would get to this intermediate, so like let's go back to the ester, right? When we get to the past, we get to OLI. O minus would always kick off OR, right? Oxygen was always kicking off oxygen, right? Because when you think about which one is, more basic, I suppose, it seems kind of obvious that, we can easily just kick off the OR group, or, oxygen just kicking off oxygen. My point being that, whenever we did these reactions, it was mainly just kicking off oxygens and everything was oxygen. We didn't really have to think about who was the leaving group, is my point here. But now, what do we have? We have an oxygen and a nitrogen. Oxygen and nitrogen. Now, it's very easy to get stuck in the lull, right? It's very easy to immediately just do this and say, hey, that's what's supposed to happen, and get to the aldehyde, right? Very, very tempting. But in this case, we have to think, who is the better leaving group here? Or who is going to be more motivated to go ahead and leave? And it turns out that actually oxygen is going to be who is motivated to leave, okay? And so how does that happen? Or there's ALH3 here. So what we get is this here. But the reason why oxygen is motivated to leave is because think about the pKa of N minus and of O minus, right? Remember, what are the values that I gave at the beginning of the video? This is 15 and this is 35. So who is the better leaving group by a large margin? It's always O minus. So in the past, when we didn't have to care because both were oxygens, so we could just kick either one off, we could just do anything, right? Like I just said, we can kick any of them off. When it comes to the amide, though, we are not trying to kick off N minus. Sure, we did kick it off in hydrolysis, but we didn't really have a choice, right, to move forward. To hydrolyze, we had to kick it off. And there was a way to stabilize, right, that N minus when it came off anyways, to make that very stable carboxylate. In this case, though, right, we're not going to have that same sort of stabilizing moment. So it's just better to kick off the oxygen rather than kick off the nitrogen. And how do we do that? N drops lone pair and kicks off O. And so one of the weirdest moves that we have seen, right? Not very familiar with it, but it's what ends up happening. And we get the iminium. Iminium is a carbonyl with a strong charge on there. And we have what? Lithium OAlH2, or sorry, H3. So what's going to happen? Iminium protonated, it's like a protonated carbonyl, right? It's going to it's going to react with the lithium anhydride, those reagents or those equivalents that are left. Again, even at 1 EQ, we still haven't used up all 4. We still have 3. And what we get is the formation of an amine. And not just any amine, right? If we look very carefully, if I kind of spin this, what we form is the amine of the original amide, where essentially the amide has been shaped off. So the amide was here, right? essentially we shave off the amide and we get our reduction. So amide reductions are actually very easy to visualize because you're literally just doing this, and that's your answer. Okay. And that's what we would get. Now, again, if we wanted to have a more selective reaction, right, because again, this is a complete reduction. Maybe that's not what we want. Again, we're going to have to use Dibble. Okay. And just a reminder of how Dibble works, right? It first conjugates, or not conjugates, but it first complexes with the carbonyl. But for the sake of simplicity, we're not going to do that. Oops, sorry, not that way. And for the sake of time too, I don't want to keep going over what I think is right and what Nasseri thinks is right. Got time for that. Okay. But again, what are we going to form here? We're going to form this complex here, right? This tetrahedral complex. And again, before it didn't matter who we kicked off, but now it does. Nitrogen's going to kick off oxygen, not the other way around. Okay. And what that results in is an iminium. Okay, it results in an iminium. Now, recall again that we have an iminium and we have an amide. Who is Dibble going to react with, right? Who has more electron density in their pi bond? It's the amide. So we never have to worry about the iminium reducing again to the amine. Okay, it's not what's going to happen. But again, to remind you guys, in reality, that's not really the case. The complex that tends to form with Dibble on here like this, this tends to be way more stable than originally thought, and it's hydrolysis of this that gives us the aldehyde. But in this case, hydrolysis of the iminium gives us the aldehyde, plus it gives us the amine. So don't forget that. We get the amine. Hydrolysis of iminiums give us an aldehyde and a amine. So don't forget that part there. It's a very common thing people forget, is this part here. Acid condition means a protonated amine as well. Okay, so we do have an ability to stop. Amines can also react with Grignards, right? But again, typically doing this reaction in excess because what we're trying to accomplish is a complete reduction. Now, if you look up this reaction on the internet, you'll get an answer that doesn't really comply with what you're going to see me do here. And the best way that I can explain why it is that we see this different answer, and I'll tell you what it is because Nasseri really cares about concepts and ideas that align. And I think it matters more to her that you kind of clump together, that, Grignards can kind of reduce everything down to tertiary alcohols, much more than she cares about, you knowing this niche fact about amides and Grignards. So if you look this reaction online, what you'll learn is that actually Grignards and amides make ketones. But Nasseri wants you to put the alcohol answer. And again, it's more of just concepts over strict memorization of these like niche facts. There's actually a way to make ketones a lot more efficiently from amides. And this guy here is known as a, you guys can skip this if you'd like, but this here is a Wainreb amide. Okay, a Wainreb amide. And so the important thing about a Wainreb amide is that if I react with like RMGBr, for example, because of a very, very specific thing known as a chelation model, right, or how the metal interacts with the Wainreb amide, we actually prevent over addition of Grignard, and we specifically get ketones. Amides, Wainreb amides are actually a very good way of making ketones, but we just don't teach it in this class. I like to actually show you guys because think it's pretty cool. But the OMe is very, very special. It causes this like interesting complex with the whatever metal you're using. I guess if it's like MgBr, just like this and this. If it's Li, right, it does this and this. And it's this complex here that helps prevent over addition. You can look more into this if you're interested. But you know, totally up to you guys. Oh shoot, sorry. Oh wait, no, sorry, it's not this. I forgot, it's not the amine that does the complex. It's the so when this adds on, the OMe is like in the OMe is like in a perfect position. Let's say it's like Li. This is what it does, sorry. Not what I showed before. It does this here. And I think it's not until you hydrolyze. So it's basically this is stable. It isn't until you hydrolyze that it does a electron movement. If I had to guess, it's probably this. That's what I would do, right? Or it's the other way around. No, it's probably this way. It's because, yeah, I think it's this way. And it's this quench here, right? It's this quench here that gets you the ketone. And you get the this O-methoxy amine here, like that. Again, you don't need to know this for your exam, but I think it's just pretty cool to teach you guys, right? Something new, something novel, maybe impress in this area on your exam by using it. But in general, in this class, what you're going to do is this up here. So I'll put this in a box. If any of you are willing to risk your grade, you can use this synthesis. It's actually not that hard to make Wainwright amides, acyl halide, and so like it's like the normal amine synthesis. You just add in this part here, and it makes your Wainwright. I'm not really sure why no one teaches it or why she doesn't teach it. It's like such a better way to make ketones from amides. Anyways, point being, there is a way to do it, but you know you're taught that there isn't because the only way that you have learned is that an amide can react with. So Gilman is that ketone reagent, right? This is not going to work. It can't react with it. So in your minds, you can think, if you'd like, that there is no ketone synth, but I would like to open your mind to yes, there is, right? Because that's what I think is my duty, is to show you the truth. Okay, but these here are the reductions of an amide. Okay, and they're fairly straightforward. I think this one's actually pretty visually is really nice because all you've really done is just, if this was the original amide, you've erased the carbonyl. So it's like a lot more visually appealing than the others. Cool. All right. So again, I mentioned that I'm specifically using the N-dimethylamide. And the major reason for this, again, has to do with the fact that amides, like if they're primary or secondary, they have this pesky acid base that's going to happen if I introduce any level of basic nucleophile. And so if we mainly think about the reductions, you know, when it comes to like hydrolysis will work. Remember, hydrolysis is a reversible process. So eventually hydrolysis will work and you will get the carboxylate and NH3. So this does work eventually because all acid base are reversible, right? But when we think about other basic reactions, such as our reductions, so let's say we have lithium aluminum hydride, just like with the carboxylic acid, which I'll use as a counterexample in all of this, right? Lithium aluminum hydride, in the same way that the first thing it does is attack a proton, right? It's going to do the same thing on the amide, right? And so with the carboxylate, right, and the amidate, right, we get those ions first. Now, it's not to say that we can't reduce. Remember, lithium hydride is like the mother of reducing agents. It will destroy anything. And so we will get eventual attack on both of these systems, and then eventual hydrolysis, right? Or sorry, eventual reduction. So this will eventually go down to this, and this will eventually go down to this. Okay, but when we think of like Dibble, for example, maybe try this on your own once. Like, how do you think Dibble is going to react, especially if we're at 1EQ, right? Is Dibble going to reduce? Is it going to, what's it going to do? So remember, the first thing that always happens is that we're going to get an acid base, right? That's what we saw first. And so with Dibble, we make the amidate. And with the carboxylic acid, we make the carboxylate. But at 1EQ, where there's only one hydrogen, the only thing that's going to happen is this acid base. And so Dibble only has the ability to, deprotonate at 1EQ. Now, obviously, if this was an excess, we can continue reductions because Dibble is the same as lithium anhydride. It just, instead of 4 equivalents of H, it's 1 equivalent. So excess Dibble will reduce both of these down. But what's the point? Why not just use lithium aluminum hydride then, right? Because lithium aluminum hydride has all 4 hydrides. Why waste Dibble, right? You need like 2-3 equivalents of Dibble, and you can just use 1 equivalent of lithium aluminum hydride, right? Don't be wasteful. So if I use Dibble, it's only really good as a reducing, a reducing agent. Sorry, as a base, not really even a reducing agent. Okay, you can say the same thing about LIPA too, if you'd like, right? Although I don't know why you would use LIPA when Dibble would be better for these guys. The same thing with LIPA H, right? It's only going to do a deprotonation. So these guys are a little, again, annoying a little bit because that deprotonation can stop a lot of things. But if we use, again, the mother of all bases, we can kind of destroy everything. Okay. This also holds true with the Grignards, which I mentioned before too. So I mentioned that, really there's no reason to be limiting Grignard reactions, but you could if you wanted to. I'm going to use a secondary amine or primary amine just because, I'm mainly using, oh no, sorry, this is secondary. I've been mainly using primary, but let's just use secondary so just used to seeing it. But let's say I had RLI, right? What is RLI going to do? Let's say at 1EQ. At 1EQ, it will take off the protons, right? It will just take off protons. Because that's all it can do. What else can it do? It's just going to do the acid base. That's literally it, right? But at excess, for example, an excess with an amide probably will destroy it. Yeah, I want to say that it will. I think you should really ask Nasiri on this because it's, again, her class, not mine. But ask her how she might feel about this one. I'll probably update the description or put in the comments like what she says. But in excess, yeah, Grignard could probably destroy both of these, or organolithium can probably do it. Probably has nothing to worry about here as well. So bases, again, any highly basic situation is always going to deprotonate on the OH and the NH2. We mentioned that in the reactivity section in the beginning too. That's what makes them really annoying and pesky, right? And it's what kind of prevents a lot of reactions with them. So one thing that I didn't kind of talk about is, the enolate capabilities of NH2 and carboxylic acid. But what really is the point of making these enolates when, let's say I use LDA, right? When I use LDA, the first thing I get is the amidate, or the first thing I get is the carboxylate, right? I could use another unit of LDA, but what's the point? I'm being wasteful of LDA. I'm making, enolates that aren't, that great, right? Both of these are really, really, unstable. Probably, it's probably incredibly hard to make this one. So I don't even think you would ever want to make it. But the enediolate of the carboxylic acid, like what's really the point? Really, this is where a lot of the conceptual question will come in, is seeing if you can understand how a carboxylic acid reacts with 1EQ, with like Dibble or RLI or LiALH4. Okay, so really understand this difference here. Now, although the carboxylic acid is low-key a little useless when it comes to, a reaction, because once the carboxylate forms, only lithium aluminum hydride can really destroy it. There is one use of the amidate, okay? And that use is specifically in the primary amine, okay? This reaction is going to be the Hofmann rearrangement. And it involves Br2, NaOH, H2O, okay? Now again, basic solution, what's the first thing that happens? We take off this proton. And we form that amidate. Now, once we have that amidate, right, we're going to have Br2 here. And just like with other enols, right, or other alpha charges to a carbonyl, that enolate can attack bromine. And what we get is an N-bromoamide. This here is specifically N-bromoacetamide, or NBA. Okay. Now, I'm gonna be honest, I'm not much of a hooper, but I do know how to 3-point shot a nucleophile into an orbital. Would that work? Is that good enough? I don't know. I tried. Okay, but if you ever, if you're having a hard time, right, getting a nucleophile in the right spot, I can definitely do it. Definitely a good nucleophile hooper. Okay, that's me right there. I'm really short, like 4'6". Anyways, bad jokes. Someone will appreciate it. Someone will. But this is N-bromoacetamide, and N-bromoacetamide is actually a very powerful brominating agent. I use it if I need to put bromine on something. It's a little fun fact there. But N-bromoacetamide, you might remember when it came to brominations in base, they were kind of hard to stop because we could not, not only could we take the first proton off very easily, but we could also take the second proton off because, again, the amidate has a pKa of like 15, right? But with the added bromine there for the inductive effect, right, the bromine makes it way more easier to pull off that proton. So the second proton probably falls off even faster, okay, than the first one. Now, here's the weirdest part of this reaction, and probably the part that, most of you didn't know about. But when we have this here with the N-bromoacetamide, bromine can actually leave. So if bromine is leaving with electrons, okay, so maybe let's track electrons real quick because you guys should be able to, follow along. Okay, so how many electrons are around nitrogen when it's neutral here? You count each lone pair electron and one from every bond. So 1, 2, 3, 4, 5, right? Remember, nitrogen normally has 5 electrons, so that's why this is 0. 1, 2, 3, 4, 5, 6. If we go from 5 to 6, that's -1 because it just gained an electron. So when bromine leaves here, and we have this here, 1, 2, 3, 4, 5, this is the same as this state where it's 1, 2, 3, 4, 5, but it has no charge, right? And it feels like it should have a cation because bromine just left, but it didn't. This is a sextet, right? 1, 2, 3, 4, 5, 6, right? Because 2 for the bond. It's a sextet nitrogen, not an octet, and it has no charge. The last time we saw this was with carbons, right? 1, 2, 3, 4, 5, 6. And these were known as carbines. So if we're so creative, what do you guys think we call this nitrogen here? We call this a nitrine. And the same way that carbines were incredibly electrophilic, nitrines are also very electrophilic. They will be attacked very, very easily. Now, think back to this. This is known as the Hofmann rearrangement, right? Imagine you have to reproduce this on an exam, this mechanism. How can you remind yourself what to do next? Well, it's a Hofmann rearrangement, and we just said that the N is super electrophilic. It wants electrons. So what on the acetamide could rearrange, right, to give the nitrogen an octet? Well, it's not going to be the carbonyl. The only thing left is this carbon here, and that's what's going to happen. This carbon will actually attack nitrogen. This is where the rearrangement comes into place. And what we form is going to be the following structure. And we're going to regain that minus charge. This is, it's either a cyanate or an isocyanate. I can never really remember the name, if I'm honest. But this here is a cyanate. Okay. And it has this resonance form here, so that it's a little more neutral. Okay. I guess it should have like a little bit of it. Yeah, there we go. Okay. And isocyanates, as you can see, it's a carbon flanked by an oxygen double bond and nitrogen double bond. So if we had, let's say, like water, right? Or actually, there's OH minus in solution. So we can just OH minus. If OH minus in solution, like where is OH minus going to be attracted to? Probably that really electrophilic carbon, right? And who is the better electron sink? Is it oxygen or nitrogen? It's going to be oxygen. What we're going to form here is this following structure. Okay. Now, looking at this, it looks really ugly, but kind of hone in on this part here. You can see that there's a C double bond N and an O minus. Focus in on the O minus with the double bond. Where was the last time you guys saw an O minus and a double bond? Right? When I draw this, does this, does this fire any neurons in your brain? Hopefully it does. That is an enolate. And enolates can tautomerize, right? They tautomerize to form ketos. So what we're going to do here is basically a tautomerization where the minus comes down and the pi bond grabs like a proton from water or something. Yeah, water will work. And what we get is the following. Okay. Now, the next part of this is, the interesting part. How do we resolve this weird structure here? This is known as a carbamate. Carbamates are pretty unstable in that they can, decompose very quickly. And the way that they do is OH minus grabs this proton. This is the way that I've learned it. It might be different than what Nitrile does. When we have this here, this O minus can come down to form CO2, and then this N minus gets electrons. Okay, so we'll have N minus. This will immediately grab a proton from water. And what we get is NH2. Okay, so I want you guys to look very carefully, and I'll even rewrite this a little bit. But when I look at the starting material and I look at the end product, what is the change? Like, what is the change that occurred? The change that occurred is you literally, so if lithium aluminum hydride just shaves off the double bond O, Hofmann rearrangement shaves off the carbon also. And what it leaves you with is carbon nitrogen. You are literally removing the carbonyl altogether in this reaction. Okay, so let's say we had this here. We're going from this to getting rid of the carbonyl so that you only have this. And one of the coolest features of this reaction is that if there is stereochemistry, let's say there's a wedge there, that stereochemistry is retained in the reaction. So the stereochemistry of the migrating carbon is retained. Okay, so this carbon here retains its stereochemistry as it migrates. Pretty cool, right? Probably not something that you've seen before. Now, I'll get into this more in the synth guide, but what's really important here that might not be very obvious is what this essentially means is that if you have any derivative that is capable of turning into an amide, so basically every derivative, because all derivatives can turn to amides, you can turn that derivative into a primary amide. So that's actually another thing too. Notice how we deprotonated once and twice. You need to have a primary amide for this to work. But if I can turn to a primary amide, I can basically turn that primary amide into a primary amine. Synthetically, what that means is that any acyl group then, any acyl group can be completely transformed into an amine. This reaction is going to be very important, and we'll see again in the synth guide how we can abuse this transformation. We can turn COX, where X is any derivative, into N. That's crazy. That's actually very crazy. And again, you'll hopefully understand later on why it is as crazy as I'm making it. So that's, the one useful reaction with the amidate, right? But in general, right, think about that acid base, right? Think about these acid bases and when they could happen, right? Little food for thought for you guys. Now, there's one last reaction with the amide that we went over in chapter 19. But remember, if we also have a primary amide, we can dehydrate it. Right? If we take out H2 and O, what are we left with? We're left with the nitrile. And so the nitrile is the very last derivative that has some importance to us. We can hydrolyze an acid, or we can hydrolyze it in base. Okay. So let's see what the acid mechanism does first. You might remember I said that nitrile protonation is like one of the hardest things to do, because it is. As such, it's like a negative 10 pK. But once it does protonate, right, water can attack it. And what we get is this here. Do you guys recognize that? Look at that for a second. Do you guys recognize that? You don't? Okay, that's okay. Well, actually, I messed up. This should have been this. And then we do a proton transfer. And then we get to here. But that's okay. Let me go back here. Do you guys recognize something very, very similar to that group on this page? Maybe pause and try to look for it. It should remind you of this down here. Remember how I mentioned that this was synonymous to O- with a pi bond? Well, if I look here, this is just OH with a pi bond, which is an enol. And what do enols do? They tautomerize. So it's very likely, well, it's not that it's very likely, but it will tautomerize. And look at that. Hold up. What just happened? It looks like nitriles are amides in disguise. So all the nitrilotrons are going to roll out because they are amides in disguise. It's late. That's why I'm making really bad jokes. But this is what I was mentioning before, back here when I was saying that, nitriles don't really have a leaving group, but we will see that they kind of do have one. It's because they're essentially amides. And that's what makes them so terrible at reacting. Okay. And so you can do the rest of the amide hydrolysis if you'd like. So in basic media, right, you should not be surprised. But again, OH minus, the attack here is probably the hardest thing to do. We'll have N minus here. We'll have a proton transfer. Again, show it complete. Don't do it like how I'm doing it, just because I earned my right to be lazy, so you guys need to earn yours. We get a basic tautomerization. And what we get is an amide that will continue to hydrolyze in base. So nice thing about nitriles is that you already know half the mechanism. You just need to learn the other half. And this is what we tend to see. Okay, but again, other than that, nitriles aren't really, they can't really react much with nucleophiles. Really, the only way to get a nitrile to react with anything, this is actually known as a Ritter reaction. But if we have, let's say, H plus here, the alkene here will react to make the tertiary cation. A nitrile won't react until there's like a cation. And like in this reaction, the Ritter. And what we get is this. Now, acetonitrile here, again, motivated by the cation, when it attacks like this, notice how it has a cation on that end. If you hydrolyze this, you can turn this into an amide just like that. Okay, so pretty cool reaction here, the Ritter reaction. Okay. Oh, just a little bit of a reminder, I guess. Just remember that an amide and acid will make carboxylic acid and ammonium, right? Because this is a primary amide. And base, it'll make carboxylate and amine. Okay, a cool little thing here with the nitrile. This is like one of the few reactions. Another reaction you don't really know, but I want to show you. It's known as the Ritter reaction. There's actually a greater importance to this reaction here that you guys maybe might not know yet. But yeah, this is an interesting one. Cool. When it comes to reduction stuff, nitriles are actually really interesting. Let's do the reaction with lithium anhydride, as we've been doing all night with every derivative. But we'll get to this point here. This is where things get a little interesting, actually, because when we get to this point here, again, the nitrogen is an anion, right? And so you might think that nothing really happens next. It kind of stays the imine. But it turns out lithium anhydride is actually strong enough to even attack here and form a dianion on the amine. Which was, again, it's a very uncomfortable thing to do sometimes. But this dianion amine is what gets quenched. And what we result in is a CH2NH2. Okay. Again, this mechanism does feel really weird, but it's okay. I don't think the nitrile one has been proven yet. Maybe I'm wrong about that. But I know that this is like a close guess. This is what I've seen, at least on the work of it. One thing that might ease you is that notice how I'm drawing N bonds with the metals. So these anions aren't naked. It's not a true N2 minus. So it's not too bad. But notice how on the nitrile, right? All I really do is I turn this into this here. So I do 1, 2, so 2 carbons of nitrogen, and I just turn it to NH2. So it's kind of like the amide in a sense. It's like really simple to see how that transformation occurs, right? Not as complicated as other things. But what is truly the most significant reaction? Actually, I guess let me mention this first. So Dibble works here too. Again, same thing. Like this is the hard part, right? Is the, adding of the Dibble on. But once Dibble is on, let's actually just do the reaction. Like with this is just fine. Again, there's really nothing that can be done. Once we get to this point, the quench is what we care about, and that quench gives us the aldehyde. Okay, so Dibble can, again, give us the aldehyde, but what really is significant here is the reaction with the ketone, or the reaction of the ketone. If I react with MgBr, like RLI, okay, so again, Grignard being strong enough to sort of attack on its own like that. Okay, again, I get to this point here. Well, the interesting thing is that, again, in the quench, or, if you look at the Dibble intermediate and this one, they're kind of the same, right? This will actually quench to a ketone. So notice how these are the same, how it kind of stays in place. The nitrile will also go, hydrolyze. Sorry, the imine here will hydrolyze to the ketone. Now, you're probably wondering why do I keep saying that, and what's the importance of that? Because I want you to think back, right? I know I told you the amide can do it, but again, think that the amide cannot make we have to think that the amide cannot make a ketone, right? But amides can make ketones, right? To our knowledge currently. Esters can't make ketones. Oh, why did I write ketone there? Sorry, that should be alcohol. I already know I'm gonna have like a million comments on that. Okay, so ester can make ketone. anhydride could make ketone and acyl halide could make ketone. Point being that there was only two guys that can make ketones, right? And they were both, they're both super reactive things. But the nitrile, the most stable out of all of them, could make a ketone. The importance here is that nitriles are stable, right? You don't have to worry about them reacting with everything in the air, like acyl halides and anhydrides, right? Or really halides in general. The reason why we hate using them is because they will react with air. They will literally react with air. You need to, I'm pretty sure you run these reactions under like some inert gas. So in lab, what we'll do is, like, let's say that we have a round bottom flask here and I have it capped, right? It's capped. So I cap it so no air can get in. What you have to do is you have to put in a needle, one to relieve pressure and one to put in like some inert, atmosphere. And then you do your reaction in that inert atmosphere. And honestly, I hate doing that. Like, it's such a tedious thing, like making sure your reagents don't react with air, especially like there's some reagents that if for 1 second they even touch the air, they will ignite. It's going to ruin your day, right? No one wants to deal with that, right? We want to do safe reactions before we ever do any hard one, like any, hard or unsafe ones. So when we want to use an acyl halide anhydride, sure, we can use them and we can make a ketone, but why not just use a nitrile that's a lot safer, right, to handle? Maybe it's safer. I'm assuming it's safer, to be honest. I'm not actually sure if it's safer, but let's assume for the sake of this argument, it's safer, right? It's more stable, it's safer, right? And it gets you exactly what you want, right? No willy-dilliness, right? Like, it's going to do exactly what you want. This is really the significance of the nitrile. Okay. And actually, imagine that, like, let's say you have an ester and you need to turn to a ketone. Again, you can't just use RLI here or RMGPR. So that's just going to fail, right? That's not going to work at all. But imagine you turn it into a primary amide and then you turn to a nitrile. Then you can make the ketone, right? I guess you can make another argument too, right? You can say, oh, why not just turn into a carboxylic acid and then turn into a chloride? You could do that too. But again, what would you rather work with? Something that needs you to make sure it doesn't explode, it doesn't explode your flask, or something that's probably going to be a lot safer and not explode your glass? I would rather go down this way. Okay. So NH3H plus, SOCl2. There we go. Boom. Got the ketone, right? RMGPR. Remember, you can't just do this. That's not going to work. Not going to work at all. Okay. So, very important. When you think of how to make ketones in this class, you're going to want to remember R2CuLi, right? And RMGBr. But remember, this is only for nitriles. And this here is only for acyl halides, and then technically anhydrides. Okay. Really the only way to do it. And again, if you really want to impress your, if you really want to impress in this theory, I can think of one of you will be capable of doing this and get away with it. But you can use a Wayner Amide if you like. That's probably better than all of these options. All right. Well, with that conversation having been said and done, that's it. That is chapter 20. Cool. So that's all the midterm material for midterm 1. Hopefully you guys found this helpful. I made a bunch of little small mistakes, so I would imagine if I made others I didn't catch, so definitely leave them down in the comments and I'll address it. If there's too many of them, maybe I'll just remake this all together. I don't know. I'll think about it. Things to look out for later in the week, I'll get out synth guide. That's probably going to be closer to midterm. Expect this on like Tuesday night of the week of the midterm. I'm working on the practice guide currently. I'm compiling questions together that I think would work well for the practice guide. So expect this Saturday at the latest, or even maybe Sunday. Hopefully by the weekend it'll be done. Synth guide won't be done till like Tuesday. So I'll put weekend here. This will be done Tuesday. The week will be on Tuesday, the week of the exam. And then NMR gallery, I literally will probably do this on Wednesday. Maybe Tuesday, I'll think about it, but really there's no like Actually, maybe I guess maybe this should be Monday. Okay, that's all I'll keep myself to. So weekend, Monday, and then we'll make this Tuesday. And more, I cross my fingers that you guys will do well on that. Who knows, right? Cool. All right. Any questions? Please let me know. Have a good night, guys. See ya.